really welcome everybody here to law, especially former students and postdocs and colleagues. One of them coming downstairs right now, who have come from far away for this event. We really, really appreciate it. It's just an amazing collection of people. So we're here to celebrate the life. This is not a sad occasion, it's a happy occasion to celebrate the life of our departed colleague. And I think everybody can say, this is one of the really great and special people, a hero to many of us. For the students and postdocs, and there's some here from currently in the department, this is a rare chance. You've got in this audience some truly remarkable people who have gone on to do amazing things after working in the McConnell lab. It's really a rare opportunity to get to meet them. I encourage you to do it. If we could turn on the lights just a little bit, that would be great. So I thought I would just start out just a few short comments, and I'm going to keep them very brief. A couple of pictures here of Harden from different stages of his life. This is a picture that I had somehow on my archive, very familiar to some of you. What's maybe not so familiar to people who weren't here is these keys. So for those of you who are here at Stanford, you may remember Harden would typically sit right there in this room, and he would come in and make a very, very loud noise with these keys. His keys, these are red keys. You could pretty much, it was an inverse correlation between the quality of the seminar and the sound coming from the speakers. The sound would get louder and louder. You knew you were in trouble, and there were occasions when he would just stand up and walk out. He was a tough guy. He was an amazing human being. I think everybody here knows that. So, of course, it was a tremendous body of work. And though I'm not a great fan of citations, I'm not sure you can actually read this. I thought I would put this up, because I just did this, quick Google search. And what you see is that these are just the first, 15 papers, all of which have more sightings, in fact, than almost all of the people currently in the chemistry department. It's actually kind of remarkable. And if you look at them, some of them even involve some of our guests. So there's, Wayne, but many of them involve Harden himself. And of course, those of you, especially from the Caltech days, will appreciate that Harden was very, very much doing theoretical work as well as experimental work, and that work, of course, has had a huge impact. So I think, Harden was, for me at least, as serious of a scientist as I had ever met. He was just totally and completely focused. I first met him as a graduate student because my own PhD research had something to do with his work, and I actually greatly admired this particular slide. So this comes from a paper from 1956 from McConnell and Weaver. This is a very famous paper having to do with electron exchange in between cuprous and cupric ions. So this is actually, if you like, an inorganic thing. It sort of came from the Norm Davison days. And what's amazing about this is not only was this look like it was hand-drawn, but you can see that the chart ran out in the middle of the experiment, and it just didn't bother him at all. Okay, this simply ended up in the literature exactly this way. In fact, all this stuff is this is cut and pasted from this picture. So imagine submitting a thing like this now. You would have a hard time. So the speakers today that we have asked to come are just representatives from different stages in Harden's life. We've asked them to do something really difficult, which is there will be some nostalgia, some reminiscence, but the real focus here is to be on Harden's scientific work as it evolved. Many of these people have gone on to do quite different things, and so of course we're all used to giving talks on what we did last week, not necessarily what we did 30 years ago, but the fact is that what we're trying to get a sense of here, I think it will be nice for the people here who are at various stages of Harden's life, it will be nice to hear about the work he did. The loyalty among alumni of the McConnell lab is something just absolutely extraordinary. It's just, from my point of view, something almost unique. And I think it's because of this focus, and it wasn't just a focus on science, but it was clearly a focus on the people who work with him. So there's one person who couldn't be here today and very much wanted to be and was going to be one of the speakers, and that's our colleague, W.E. Murner. He asked me to read a quick statement from him, so I'll do that. He said, "I deeply regret that I cannot be with you all today, but I am here in spirit in remembrance of Harden. He was a true giant of physical chemistry whose influence spanned many decades." And we've seen all these decades here. "I was extremely privileged and honored to have collaborated with him a bit on single molecules and membranes. His approach to science, especially his persistence and perseverance for many decades after his Festschrift, classical what he started, have been a deep inspiration for me. I was particularly impressed by the brilliant way he could attack tough problems. He had an uncanny ability to address complex data by generating a few key concepts, and then he would apply theoretical and computational analysis to obtain deeper understanding. I also remember clearly how he nurtured me as a younger colleague. He would always ask about my latest results and papers. All of us had that experience, and sometimes we didn't have much to say. I am forever indebted to him for the many times he nominated me for various awards. There must have been one there. And he even took several papers and actually read them before writing the nominations. I will miss him greatly. I think that summarizes, the sentiment of everybody here. Just a few housekeeping things, because we have many people here who haven't been on campus for a while. We have maps outside. We don't have much time in the morning, but there'll be a fairly long break around lunchtime, and the sun's going to be out. I encourage you to walk around. This is where you are, here in the Mud Building, and those of you who are students here, as opposed to the Caltech group, you were in Stauffer 2, which is probably not long for this world, neither is the Mud Building, by the way, and in the Gilbert Building, which is in biology, that building will probably survive the large changes. In case you haven't noticed, there's been a lot of changes on campus, and they are everywhere. It's very easy to get lost now. Just remember Hoover Tower is there. Okay, that's the key. For visitors, I urge you to wander around. You may find it interesting to go over to the museum. There's a particularly nice new museum that just opened very recently, the Anderson Collection, which has a quite spectacular collection of contemporary art, which you may or may not like, but I think you'll find it, it's unusually high quality work. So the events today couldn't have been done without a lot of help. There are two people you've probably met, Sejan and Alicia, who are outside still and worrying about things, and those are two people you can go to, or myself if you have any problems. But the real co-conspirators are sitting right here, Hayes Griffith and Alvin Kwiram, who have been sort of my mostly email, but like maybe 10 emails per day, co-conspirators in making this happen. And I thought I would end with this picture which sits on my wall, which is, I also don't know what the provenance of this picture is, but I particularly like it. I think probably Wayne knows more about this because he's told me some stories about these weapons up at the ranch. But this is exactly the way I feel a lot of the time. And so I think it's a very nice thing. If somebody knows who took this or what it is, it would be great. Anyway, Keith Hodgson's the chair of chemistry. I thought he would just say one or two words of help.
So really, it's a great pleasure on behalf of the Department of Chemistry and on behalf of Stanford University to welcome you all. There's little that I can add to what Steve so eloquently said about Harden, and I'm sure many of you, like myself, treasure the associations that we had with Harden in many different ways, as students, as postdocs, as colleagues on the faculty, both here and of course at Caltech. I just add one personal note. I think one thing that perhaps struck me about Harden, I came as a junior faculty member to the department, and he was a tremendous mentor. His personality, he was a tough guy, as Steve said, but as a person, there was a quality about him that was really quite remarkable. And as a junior faculty in the department, where tenure hadn't been forthcoming very frequently for many years, I found him really very helpful in providing advice to me, and I'm sure to others as we evolved in our young careers. So that was an association with Harden that I will remember for forever. I'd like to thank one more person, just because he thanked everyone else, and that's Steve. Certainly within the department, the devotion and dedication and effort that Steve has put into this, I think will be well reflected by the program today, and I'm sure that everyone will get an awful lot out of it. And we hope that it will endure, not only through the recording that's being done, but hopefully through an enduring lectureship in Harden's honor, which we're seeking to endow. So let me end just by coming back to this previous switch. You must have had it on some. Back to this one, and this is not to do with Harden, but it's to do with the fact that you're all here. But in part, the fact that some of you were here many years ago, or over the past couple of decades. And what I was going to say here is, if you look at this area of the campus. Here's the mud building, which, as Steve said, will go away at some point, as will Stauffer 1 and Stauffer 2. The point I wanted to make was, here's the old chem building. And some of you knew it because that's where the offices were when you were here. The chem office was there, there were labs there, there were lecture theaters there, the library was there. That is being completely renewed. And you can't get into it because it's a construction site. You can walk around the outside. But it will become a new, modern center for teaching and learning shared between chemistry and biology. And it will open roughly a year from June, graduation a year from now. And it will be a fantastic facility, which we will all welcome you back to see. But it does highlight one more small thing, and that is that this area of campus around where we are located is being thought of by Stanford as the new chemistry-biology quad. And so we are a central part of that quad with biology. And I'll end by saying, note that just to the north of us is the new Arts District. That's what Steve invited you to walk around. Across the street is the School of Medicine, and this is the Discovery Walk that goes along through the School of Medicine buildings. It's really a nicely done part. And then to the south of us, of course, is engineering and other parts of campus. Of course, the central part being over here. So there are a lot of changes, and I think we're really privileged to be a part of that. And I think Harden would have been impressed had he been able to see the central role that chemistry is playing in this part of campus. So with that, I said probably too much, but I want to say thank you again, Steve, and all of you for coming.
Thank you, Steve. Well, I want to add my welcome to that of Steve and Keith. And I particularly want to acknowledge Sophia and Jane and other members of the family are here as well. We're here to celebrate, of course, someone whom we all greatly respected and admired and had good and bad times with. And it's wonderful to see so many of you here. I know I've corresponded with many of you and harassed endlessly by my emails, but I much appreciated your responses. And of course, many others here who have not suffered that because you're not part of the McConnell group, but you respected him and worked with him. And that's part of what we're trying to celebrate today. This picture was taken in 1990. Harden and Sophia came up to our home for a weekend in Seattle, and we took a trip around Mount St. Helens, Mount Rainier, which is shown here, and other sites. And it's one of many wonderful memories that we have and we share, and great stories that go with some of those. We don't have time to go into that. The last time the McConnell group met was 1992. How many of you were here at that event? That's a pretty impressive number of survivors. This is the Caltech contingent. You see it's quite a bit smaller. And right in front here you can see Sonny. We're delighted that Sonny could join us here today. We made him an honorary member of the McConnell group. And because of the tight time constraints, I'm going to stick to my script. So I hope you'll bear with me for the next 10 minutes or so. In the program you received today, there is some key timeline data, and so I won't repeat much of that as part of his early life, but he completed his doctoral work at Caltech in 1951, with Professor Norman Davidson after a 2-year postdoctoral stint, and at Chicago with Mulliken, where he expanded his horizons with molecular orbital theory. He joined the Shell Development Company in Emeryville, California, in 1953. Can this be turned down a little bit? It seems a little bit loud to me. Okay?
Yeah.
Okay. Shell had acquired the first commercial NMR instrument on the West Coast, and one of only 2 or 3 in the country at that time. So Harden was in a perfect position to bring his considerable theoretical power to bear in understanding this promising new tool in chemistry. This was a highly productive period, and a number of seminal papers quickly established his reputation as a rising star. Of course, he was already well known in terms of his intellectual horsepower to his PhD advisor, and in the spring of 1956, Norman Davidson, with a couple of his colleagues, Werner Shoemaker and Professor Roberts, persuaded Linus Pauling that they should hire this, and I quote, this most exciting chemical physicist on the scene. Well, Pauling made it happen, of course, and we're delighted that Professor Roberts can be with us today. And we want to thank you for your role in bringing Harden into the academic fold. And I also want to, on a personal note, thank you for serving on my doctoral committee over 50 years ago. And getting me a bad time. Harden joined the chemistry department in the fall of 1956 as an assistant professor. He and Sophia were married that fall on October 6th. In addition to all of that going on, he already assembled by that fall an impressive group of some half a dozen graduate students and postdocs. I won't dwell on his work at Shell, except to say that in a series of about a dozen papers, he and his co-workers contributed significantly to the understanding of NMR spectra of organic molecules, including papers on spin-spin coupling and chemical shielding, which are well-known publications and have many citations, as you may have seen. But the NMR paper that had the greatest impact was the second one on Steve's list, which is reaction rates by NMR. This paper has received well over 1,000 citations, and Harden was certainly one of the pioneers in the early days of NMR. But if you want to know more about the early days of NMR, you should consult with Professor Roberts, because he knows more of the history of that than anyone in this room probably. This is a unique opportunity, so talk to him. Although Harden's first publications on electron spin resonance, ESR, started in Shell, as you've already seen from Steve's slide, in 1956, as his work in NMR was winding down, his real groundbreaking work at ESR was done at Caltech. Here, Harden clearly led the way by solving the hyperfine interaction conundrum in planar organic free radicals. The puzzle was this: how can you have an isotropic hyperfine interaction when the proton is in the nodal plane of the electron? This problem had first come to his attention while still at Shell during a visit by George Pake, who was then in physics here at Stanford. Pake was visiting Shell to see this newfangled NMR spectrometer that Shell had acquired. And Harden, in the course of some casual conversations, overheard him say that the last nail is being driven into the coffin of theoretical chemistry. As you might expect, this intrigued Harden. And later that day, Harden asked him what he meant by this, and Pake explained that the observation of a finite hyperfine interaction could not be reconciled with the fact that the proton lies in the nodal plane of the unpaired electron. Harden immediately saw the flaw in this argument, and as he recounts in his stories that Hayes and I worked on with him over the last 3.5 of his life, he says that he went home that evening and probably ignored Sophia and everything else, and worked out the basic theory to explain the observed results. In his first paper in 1956, submitted from Shell, he showed that the electron spin correlation could give rise to non-zero spin density of the proton. The essential features of what would become known as the McConnell equation were already implicit in this paper. So, this is the famous McConnell equation. where A is the hyperfine coupling constant, the observed coupling constant, and rho is the spin density, with Q is proportionally constant. This paper was soon followed by the full theoretical spin paper with Don Chestnut on the isotropic hyperfine interaction in the CH fragment, and then with Strathby on the anisotropic hyperfine interactions in oriented organic free radicals. These two papers, in bold font here, represent the foundation for nearly all ESR studies of organic radicals. Not only did he develop the theory, but with his colleagues, he developed some elegant experimental studies on single crystals of irradiated malonic acid to verify both the predictions of isotropic as well as anisotropic hyperfine interaction. The prototypical CH fragment is easily formed in irradiated malonic. Here's the two malonic molecules, centrosymmetric in a triclinic unit cell, and after X irradiation, one of the final products is this free radical with unpaired electron primarily 78% in that p orbital, and the hydrogen atom in the plane of the three carbon atoms. And of course, the hydrogen atom is in the nodal plane, and that was what gave rise early on in earlier work by people like Sam Weissman and Arun, the question of why in the world did you have hyperfine interaction in that case. So Harden had the insight to say, to determine that this dicarboxylic acid seemed like a good candidate to create the prototypical CH fragment that would represent all CH fragments in all aromatic hydrocarbons and other systems of that sort, and shows this system which worked beautifully very quickly. Hanan Heller and Terry Cole, two of the first postdocs in his lab, both of whom are now not with us any longer, verified the theoretical predictions with the malonic acid radical. These papers, plus these two foundational papers I mentioned before, plus these other papers on this list here, which are the experimental verifications, really laid the foundation for virtually all subsequent work in the entire field of ESR and organic radicals. This slide summarizes some of the other truly groundbreaking work, and if you just look at this list, I'm not going to do it, you just look at this list and see all the first unique things that he pioneered, it's really quite staggering. I'll let you contemplate that in your own time. So if you'll indulge me, I'd like to wrap up my comments by completing the malonic acid story, because this was not quite complete, as I will argue. I arrived at Caltech in '58, just as the work on the CH fragment was getting started. 2 years earlier, George Fair at Bell Labs had published a short note on a new technique that he later dubbed electron nuclear double resonance, or ENDOR. Harden suggested that I should try to observe ENDOR in organic free radicals for my dissertation project. This was a bit daunting, because it meant learning about designing and building a liquid helium dewar that could accommodate microwave cavities, learning how to design microwave cavities so that they could be run at low temperature and have an RF coil inside the microwave cavity, and of course assembling all the power amplifiers and electronics that goes with doing NMR and ESR at the same time. But we got all that done in about a year, and of course malonic acid was our target. It was the workhorse system in the lab, and that was where I started. Unfortunately, I was not able to detect an ENDOR signals from malonic. That was a mystery. At that time, Keller was just finishing up his work on the ESR of the radicals in irradiated succinic acid, which is the next dicarboxylic acid in that series, with two methylene groups, where he was able to treat the beta proton interaction, which was a necessary part for the total description of hyperfine interaction for organic radicals. So rather than simply doing the smart thing and asking Keller for a sample of his succinic acid crystal and plug it into my ENDOR spectrometer, I, of course, naively chose to investigate a more complicated system that would demonstrate the full power of ENDOR and do something that you could not do by ESR. That meant I had first of all, I had to work up the ESR of the next dicarboxylic acid in the series, the glutaric acid system, because it had 3 methylene groups, and the hyperfine interaction for these protons here is with an unpaired electron located here is too small to be resolved in ESR, but it's still finite, still has a finite value, and should be resolvable by NDOR, which typically would be 100 times better in terms of resolution than ESR itself. In any case, by 1961, I had indeed succeeded in observing NDOR signals in glutaric acid. As far as I know, this was the first NDOR signal observed in the university setting. Unfortunately, it was not the first NDOR of an organic radical to be published. Terry Cole had left the McConnell lab in the middle of 1959, and a few months later, Keller followed him to Ford Motor Company. At Ford, John Lamb had just finished building an NDOR spectrometer where he was studying chromium 3+ in aluminum oxide. Well, Keller and Cole did the smart thing. They simply plugged their succinic acid crystal into the NDOR instrument there and observed the NDOR signals in succinic. There are a number of lessons here for graduate students. I have time for only one. Do the most direct, simplest experiment to get to the answer. You can always flesh out the story later. Harden was a master of this, but I didn't learn it soon enough. The reason we had not been able to preserve the malonic acid radical in our NDOR experiments was somewhat ironic. The standard procedure at the McConnell lab was to heat the malonic crystal after radiation to get rid of some extraneous lines in the spectrum that were just interfering with interpretation. It wasn't until a few years later when Rod McCauley, who was also here, joined my group at Harvard, that he was able to solve the mystery. He showed that it is precisely the fast relaxing radical that you get rid of by heating that makes the NDOR really work well. He eventually completed the definitive NDOR study of 30 separate hyperfine tensors for roughly a half a dozen distinct radicals in malonic acid. So I'm happy to report that the malonic story was finally completed but remained in the family, so to speak. Later this morning you'll hear from Brian, who will tell you about much more sophisticated NDOR experiments that he has carried out in the course of his career. The research I've alluded to was carried out in a span of about 8 years with some 40 papers on NMR and ESR through 1961. Although I don't generally spend much time either on publication statistics and citation data, even though I'm a bureaucrat, I think it's worth summarizing the data for Harden's career. Over a period of 50 years, he averaged roughly 9 papers a year, and that body of work generated roughly 700 citations per year on average over the last 40 years. My focus has been on Harden's early work, primarily structural studies. Essentially, all that work came to an end around 1962 when the interest shifted abruptly to the study of triplet excitons. For a discussion of that territory, I'll turn it over to my co-conspirator, Hayes Griffith.
Fortunately, this is being recorded, so just a little side note. I know George Fair very, very well. I competed with him unsuccessfully on many projects, and we were once together at a meeting in southern France, and he turned to me and he said, "There's only one chemist I respect," and of course that wasn't me. Harden McConnell. That was for those of you who know George Fair, his standards were about the same. Very, 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 very similar. Anyway, so we're now privileged to have Hayes Griffith, who's going to finish the second half of this story.
Thank you for coming. I know that you've gone to a lot of effort to get here, and you're using up a whole day that you could be doing other things with. Ideally, what we're trying to is, wouldn't it be great if you left here with a new enthusiasm and some ideas about your own work so that you actually profited from this day here, as well as just remembering McConnell. That's the idea, and I think we're doing that. And what I would like to do is to discuss some of the factors that contributed to Harden's success. And of course he was bright, very bright man, but that's not enough. The other factors, some of the other factors that really played into his success were this focus, focus, focus. He was just incredibly focused on research. Without the focus, brightness just doesn't produce results. And be self-taught. He learned quantum mechanics himself from a book called Irene, Walter, and Kimball. He learned biochemistry as he needed it, and then he learned immunology, the parts of immunology that he needed. So all along the path of his career, he was learning new things. Secondly, enjoy the game. Now, you won't understand that word, enjoy the game, until you read this memoirs of Harden McConnell. And there's no spaces in it. It's Harden, no space, McConnell.org, not com. It's worth reading that because you get the feeling of what he was as a scientist and as a human being. Because he wrote it himself basically in the last year and a half of his life. Observe first and then do the math. Math is very useful, theory is useful, but Harden, he said that he had a good intuition. But in fact, that's true, but he built it on just observing everything he could. His papers, other papers, he simulated information so that he knew the answer before he started the theory. He embellished it. Of course, he made it to the next step, but he knew the answer. In the McConnell equation, I talked to Don Chestnut about this, and he saw that the splittings were much smaller if the electron was distributed. And he'd seen a polarization diagram that Linus Pauling had put up in the seminar. And he just assimilated the information so that when he set out to do theory, he knew the answer. And that is a very useful thing, to be able to look it up in the back of the book as you're working your way back. Look for simplifying principles. A equals Q rho. Published work others can use. And that's the theme that Alvin brought up, and I always also brought it up. This is Caltech as when I arrived on the scene in 1960. We've already mentioned that Jack Roberts is here, and he was a very influential and important person in Harden's life. Sonny Chan is not in this picture because he hadn't arrived yet. Other people who were important to Harden, Norman Davidson, his advisor, that penetrating stare, boy, do I remember that. And then G. Wills Robinson, a very nice man, I'll mention later. These people were very important. Of course, there are other people that were too. Two areas of McConnell work at Caltech that Alvin Kwiram has already mentioned, structure and dynamics. The electronic structure of free radicals, that Alvin's already gone over, and he's already mentioned chemical exchange, which is good because I want to talk about that for a minute. On the dynamics, this is Harden's paper that Alvin mentioned. And nearly everybody's seen this because there's textbook examples now. But at the time, NMR spectrometers were now becoming available in every laboratory in the country. And organic chemists, for example, could see a molecule in two environments would give two lines. But if they happened to have a system that they could vary the temperature or vary the pH, and they saw anything like this, even parts of it, then with the McConnell equations, they could actually get rate data without having specialized kinetics spectrometer. So you can imagine what a big input into results that was. I mean, people could get far more information out of a steady state NMR experiment than they could before. And that's the power of the McConnell equation. He wasn't the first to incorporate fast chemical or slow chemical exchange into Felix Bloch's phenomenological equations of the magnetization, how it decayed, but he did a job that was useful to other people. So try to publish papers that are useful to others. Now, today, most of the talks are going to be about success. I'm going to talk about failure. because you learn a lot from failure. And one of the misses on this was my first year at Caltech. Absolutely, and actually Harden in his memoir says it's his biggest embarrassment of his career. That gives me the lesson. And there were plenty of other exciton experiments that did work. After this was the first one that was tried in the lab. And there were plenty of other successful experiments. And I'll refer to Zoltan. Is Zoltan here?
Yes.
Okay, expert on that. Robert Metzger?
Yeah.
Where are you? Okay, another person you can talk to. So there are people here, probably some others too, that are here that you can talk to, but not me. This is a standard Jablonski diagram. Basically, shine light on the sample. We all know that you can get fluorescence out from the lowest excited singlet or phosphorescence from the lowest triplet. Now these states, these lowest states live for a while, so you don't just have to get fluorescence out of them. They can, particularly the triplet state, can migrate, the energy can migrate across molecules. Why is this important? It's a way of transferring energy. You can think of an electron-hole pair moving around in crystal. For example, today, photosynthesis, like the capture of energy by plants in the antenna structure, solar cells, this is discussed, that be present in every system, and now the organic LEDs have exciton. So this is a problem of some significance. At that time, one of the great experiments done was on triplet states, was on naphthalene. Harden looked at this crystal, and clearly he saw right away, this is an edge-on view of naphthalene, that these molecules are oriented in just two orientations. They're either like that, or they're like this. And that's true of all the aromatic molecules we crystallize them, whether it's anthracene or durine, they all crystallize like that. So in fact, even though the crystal is quite complicated looking, you only have two orientations. So an exciton hopping in this crystal is going to give that sharp line, just as in the NMR experiment. And so Harden looked at that. He did the theory later. But I'm just sure how his mind works on this. He did it. I know what that's going to do. It's going to wash out the hyperfine structure, going to give a sharp line, and we can predict exactly where that line will be because we know where the lines of these two spectra appear. That had already been determined. So, there are a couple of different ways you can do this experiment. One is doping. Now, the very famous experiment that had been done just before in Chicago was to dope naphthalene into durine. Durine is a benzene ring, so it's a higher energy molecule, so you have a trapped naphthalene. And that's what Clyde Hutchison was able to characterize a triplet state. Before that, people thought of phosphorescent state. But after that experiment, it's the triplet state, because you could see the electrons and how they interact. So Harden could have done a doping experiment, and it would have had to have been in naphthalene and deuteronaphthalene, this experiment. We should have done it. Something like that was being experimented with down the hall by G. Wells Robinson, and we didn't pay attention to it. But here's another experiment that can be done, but a very difficult one, and that is to try to study a pure molecule. I mean, there's a reason in Silicon Valley that they dope, P-dope and N-dope, and they don't build computers out of pure silicon. It's very hard to control what you're dealing with. So McConnell made the choice. He said, let's search for triplet excitons in pure naphthalene at liquid helium temperatures. Perhaps the excitons will be trapped and we'll be able to see them. Well, I've been a graduate student for 1 month at Caltech. He said, the boss said to go look for that. And Alvin Kwiram was a senior lab member looking over us to make sure we didn't destroy anything. And on my thesis, we built liquid helium viewers. We built various types of liquid helium viewers. You don't need to know about that, but I'm just saying this stuff is complex. It took a lot of work. We built zone refiners. We purified naphthalene, which is NH6, which means it's all protons around it. We designed cryogenics and ADSR cavities. We built quartz crystal optical systems. All graduate students working on it, 2 of us. And we spent 6 months on this, and in the summer, we did an experiment. And we failed to see triplet hexagons in that, but we didn't see anything. We saw the end of chart on the rolls as they came through. We didn't see anything else. And Harden, there's Harden, and he's not smiling. And actually, he took it pretty well. He pulled us off the project, me, I was the one, pulled me off the project at the end of the summer and said, you know, we're just go do something else. And he, later, many years later, he did notice that the Wolf's group in Stuttgart had done some of these experiments successfully, but he didn't give me a bad time about that. He just said, well, that's the way it is. But when he was basically got the word that he had terminal cancer, and that's when he started his memoirs, almost 2 years ago. Then he got intensely interested in going back over all his science, the impact of his science, who the competitors were, and who succeeded. Remember, he liked to play the game. And what he rediscovered at that point was, gee, they did a good job. And why didn't you do it, Hayes? So I got this email from him. He said, did you forget to run the DPPH standard? That's like saying, did you not plug in the spectrometer? So I had to go back and write a report. Exactly what we did 52 years after. And I had to search down to see if anybody in Germany was still alive. And I found one. And we discussed it, we found out what went wrong. Basically, they didn't see anything either under the conditions we were looking at. They did the dimer experiment, which was the G-Wills-Robinson one, which we should have done. And then they went to anthracene, and you don't need to know the whole story, but it turns out you go up in temperature and not down. We went down. We went all the way to liquid helium, but on a warm summer day in Palo Alto, that's when you should do the experiment. Because at 80 degrees in anthracene, they saw the signal. Now, what do we learn from this? The important lesson for graduates, and I'm not kidding when I get to this. I can laugh about the other right now, but the important lesson for graduate students, advisors don't have time to work out the details. They may have a really good idea. How many graduate students are here? All right. No. How many? We do have some graduate students here. Serious graduate students. Okay. You got to take ownership of the project. You've got to think, question, examine, innovate, assume that the advisor has overlooked something. If you don't, 50 years from now, I'm going to talk the last few minutes about transitioning to Stanford because I helped do the move along with a lot of other people. And I was around for a while at Stanford as a postdoc. Well, at Caltech, we used this molecule, frenesol, which has been around since 1845 as a standard for those malonic acid experiments to measure the splittings. So that was just a routine thing that was done. But notice what it is. It's a nitric oxide molecule here with the unpaired electron distributed over this N and O. So you get a nitrogen splitting here, protected by sulfate groups so that solvent can't get to it, so it's stable. It's not very stable, but it's stable enough to use. Now, this molecule appeared on the scene from Hoffman at American Cyanide in 1961. Same structure. It had the NO group, and it had methyl groups out here to protect it from the solvent. And this turned out to be very stable. Harden's recollection, Jack, Harden's recollection is that you gave me this sample. That's the way, I don't remember how it got into the lab. All I know it was in a box. And he said he tried to do an interferomagnetic experiment with it, and it didn't work. The spins didn't, or too well protected by that. So he handed it to me and said, go see what you can do with this. Go do something interesting. He liked the word interesting. Go do something interesting. Well, I played around. I knew a lot about this molecule. We didn't publish on it, but we used it for a lot of things. And it's beautiful, it's red. It's an absolutely gorgeous molecule. Now, all of a sudden, Stanford, this launched the era of spin labels. These were the molecules. Now, frenesol was just not stable enough. But here's diethyl nitroxide from the Caltech days. Tempo was also produced. And these are the molecules and the type of structure that actually did probably 90% of the spin labeling work at Stanford. And there was not the first experiment. Onishi from Japan turned Harden's attention to biology. Would have turned anyway, but he turned it by saying, I'm coming and I want to do a biological experiment. And there weren't any in the lab. So what Harden did was to have him do chlorpromazine interpolated in DNA. Norman Davidson was working on DNA. See these links between advisors and students. But that wasn't a general method. It was the Caltech work that produced these. And I was able to take that molecule and put it on the desk in front of the people around the table and say, this is what you have to use because it's stable. And they put the labels on it, and we were off and running. One other thing we needed at Stanford was to do theory. Well, what do we do when we do theory? We have to have some principal data. We went back to the Alvin Kwiram experiment, the malonic acid experiment. Here it is over here. I won't even say anything about it, except you can see the splittings change with orientation. We measured that, this molecule in a host crystal, just because malonic acid irradiated the host crystal, you get it. Over here, what we did was take diethyl nitroxide and put it in a host crystal, so it's dilute, and then measured the splittings at different orientations. This is the big splitting along the p orbital, the molecule, and then in solution, it all averages out. This was all we needed in order to do theory, because you could do all the simulations, except for a couple of them. You could do almost all the simulations with this much information. The message I'm trying to get here is it's the Caltech physical chemistry that launched the biology at Stanford. Who guided the biology at Stanford? It was the absolutely elegant experiments of Rupert Stryer. With his red, he was not wearing a red tie, but he always came up with a big red tie. And he gave and they were beautiful experiments because they glowed in the dark. They were all fluorescents. And he took fluorescent molecules and attached it to proteins. And it just mesmerized all of us because we'd never seen anything like that before. So we all started attaching these molecules to proteins. And that's again, then of course Harden had this genius of putting all the parts together with theory and experiment, and then looking for the simple principles and making experiments that people could actually use. In conclusion, may Harden's outstanding career inspire you. That's why we're here today. You should walk out of here with a new look at what you're doing. Focus, focus, focus. Be self-taught. Very hard to do. That's the hardest thing to do. That's why it's in the help. Everything is trying to take your time away from you. But you have to focus. Enjoy the game. If you're not having fun, you're not going to focus. Observe first and then do the math. Look for simplifying principles. Try to publish what other people can use. And for students, take ownership of your project. Think, question, examine, innovate, or you'll be like me, 52 years later. Thank you.
Well, there's the years that I spent in the lab. And I want to thank Sophie for a conversation we had just this morning, where she gave me, in a sense, permission to give the talk that I put together. Because I've been struggling with the dichotomy of the reason why we're here, and then the true joy in being here. And she said that was okay, in effect. So we're here, I'm here to celebrate his life, and to testify its impact on science. I'll talk a little bit about his impact on science, and I'll talk a little bit more than you two guys did on its impact on the people, although you surely addressed it. If we're lucky in this life, we've got 3 families. The one you're born into, you have no choice. You have some choice on the family that you create with your partner, your spouse, and your children. And if you're really lucky, you've got a 3rd family. And that's the people you work with and spend most of your life with. And many of those people are in this room. And it's at the beginning that Harden was there. I've said many times to many people that, as far as I'm concerned, everything that happened to me before my time in Harden's laboratory, that was gestation. And the person who I am, for better and worse, is and was born in that laboratory. So, several of us had a lot of discussion. What do you want to say? How much science? How much memory? How much this, that? And I've gone a little bit more towards the memory of the people, but a little bit about how Harden did science, and I think that's important. So, this comes from another talk I gave on an analogous situation. The recommendations I took, something about my interactions with Harden and the lab members, but then some thoughts on how Harden did science. And you've heard this indirectly from Murner's comments and Hayes' comments, but I'm going to focus on how I perceived his doing of science. And you'll recognize my perceptions having been echoing what you've already heard. And then I will talk a little bit more in detail about a paper of ours that just came out last year, which was fundamentally initiated by a paper Harden published more than half a century before. So, what to say, I had the benefit of having said a lot of what I want to say. And as you can see, 2006, several of us were asked to write our recollections of time in Harden's lab, McConnell and his lab. So there were 4 of us who did that, and the nice thing is we're all here. And I have to say, have you ever seen anyone look more professorial than Larry Berliner? In contrast, if you took the glasses and changed them, and changed the hair a little bit, and the cloak, that could be Cornelius Vanderbilt, some kind of a master of industry. That's what he looked like in our day. I wouldn't buy a used car from a guy who looked like that. But I sold one to him. You may recognize that's the car that made Ralph Nader famous, and I owned one. The car that was unsafe at any speed. Not only was it unsafe at any speed, it crapped out on me most of the year before I finished. It was a real piece of junk. And that's the man who knows, because I sold it to him. Full knowledge. And he fixed it all up and then pawned it off on somebody else. So anyway, thanks, Cornelius. So this is a little bit from my write-up of that time. So I thought, and I talked first about the evolution of the lab. And there's just, no, Harden didn't have one career, he had many. And any one of us would be glad for one of those careers by and large. And he didn't have one lab, and that's been implied very clearly, but because the lab isn't a piece of, a real estate, it's the people in it. And so there have been many groups that go through that. And as was noted, I was part of 2 labs, the last lab before the move and the first lab after. So I looked at the original list of speakers. And I looked at that, and many of them I've never met, yet I knew I'd seen a group picture. And yes, there's been a little inversion, but archaeology has a lot of misattributions to ages, so Wayne actually did come before Roger in the lab. So I looked, there was a group picture. Some of you have seen it, but you didn't know it was it. So there it is. So we have prehistory, Caltech and Keller, you've just seen. Doesn't that kind of look like Alvin? There's me. And I'm just poking my nose out of the water. And here's all the rest of you guys. And Caltech and biophysics, Caltech and PChem, Stanford and biophysics, that's a major change in terms of geography and in thrust. But as you've heard already, there are many changes along the way. So the early career, which you've heard about from Hayes and Alvin, and about NMR and EPR, they were basically over when we got there, when I got there. We, you'll see in a minute, are Zoltan, Marty, and Robert. I'll mention them again. Electronic structure of molecules, and I'm going to mention it, Jan Keller, that's important to me. That was in its high day, and solid state career, excitons were started. One of his other major mistakes, which he acknowledged, was high TC superconductivity. That was what I did. But anyway, so this is the lab that I was in. That was the lab, not the hardware, and not the space. But Hayes is here, and Zoltan came with me, started with me. Bob Metzger is here, started with me. And lots of other folks. And if you know the Yeats poem, where he names the names of people from the past, it's like, every time I look at this list of names, I see a face and think about an interaction. So, Shosh, Zoltan, Marty, Bob, all here. We didn't know what we signed up for. The 2 shifts from Caltech to Stanford and from biophysics, 2 biophysics from physical chemistry. And I watched it, but trust me, I had nothing to do with the transition into biophysics, but I at least watched it. So here's the Stanford lab, and there's Bob Hughes in the audience, and there's Larry, and Larry again, and Seiichi Ogawa, and Wayne is here. Another one. All right, that's screwed up. There's a paper from Marty. But anyway, and this is generally thought to be the transition paper from physical chemistry to biophysics. But as Hayes mentioned, that's not the truth. It was Sunichio Onishi's paper prior, which was the true transition paper, but all the rest of history started with spin rings. And I should say that probably the real transition person is Larry, because he's the only one, I think, that I know of at least, who had a paper from the past and a paper from the future. So a triplet exciton paper with Bob and a spin labeling paper with Bob. So maybe actually that was Larry. It wasn't. You guys could have to decide. I kind of thought, you know, a little bit. Put the glasses on and it might help. So anyway, let's talk about my interactions with Harden and then we'll get to the science stuff. So this is what I said in that summary. And it's back. You spend all your time with the lab, not with the folks, not with Harden, but mostly it's with the other folks in the lab. So why did I try to kill Marty, and why did Zoltan want to kill me for reason? Marty is an extraordinarily cultured guy, knows all operas by heart, probably plays them all on the xylophone. And he was about to launch into a doggerel version of a Mozart aria with his own words. And I knew if I ever heard those words, I would never be able to listen to that opera again. So I said, please don't do it. That is not going to work with Marty. Then I was a little more emphatic, and that didn't work. And then I started to threaten him with bodily harm and chase him down the street in Palo Alto. And that stopped him because he ran out of breath. So, okay. On the other hand, Zoltan just got early and was writing his own papers. And I was close enough to it that I tried to stumble through one of his papers. And I managed, I thought, to pretty well do that. And I said to him, you know, that wasn't so hard. And he seriously considered killing me. Because it isn't hard to take a path through the jungle that someone else has hacked out with his machete. And that was me. Zoltan was the guy with the machete. And it was only years later that I did a little arithmetic of my own that I thought, you know, Zoltan, thank you for not killing me because I deserve it. If you had, it would have been justifiable. But the best is the spin labeling. Stone was an organic chemist making nitroxide. And this was a very politically incorrect topic. So he smoked all the time in the lab. And he always walked around with a cigarette with about an inch of ash, or 3 inches of ash. And I would watch with awe and terror as he'd taken something he'd taken 2 or 3 weeks or a month to synthesize, open the top, and look in. When was the ash going to fall in? To the best of my knowledge, it never did. And has anyone here ever heard of Clarence Darrow, under the age of like 70? All right. This was a famous lawyer of the first half of the 20th century. And it is alleged, and it's probably true, that in order to distract the jury from his opponent's brilliance, he would stick a lighter in his cigar to hold the ash, and the jury would watch the ash. And I always wondered, but didn't have the nerve to ask Stone if that's what he did. But okay. So then, but there are moments with Harden, and you've heard that he could be a tough guy, and I'll mention some of that. But there's some pretty funny moments too. So Jane probably did not know of the intimate relationship between her and Richard Feynman, famous physicist. So Harden was giving a lecture in physics on excitons and was getting a considerable amount of grief from Feynman, who was heckling from the crowd. And they were going back and forth, and it was a little scary. It's like, two elks clashing their antlers. And I'm sitting in the back and I'm saying, I'm a little mouse and I'm glad I'm not in it. And then finally, Feynman said something that was a little more inflammatory than the others, and Harden just looked at him in silence. And now, time out. There actually was a day when green and red lasers didn't exist, and the physics department had, as a pointer, sitting unnoticed on the desk in front of Harden, it looked like about an 8 feet long, incredibly sharply pointed, thick piece of wood. Like a medieval lance. Harden silently looked at Feynman, with one finger, rotated this thing so that the arrow pointed right at Feynman, and the place cracked up and Harden won the game. So, I only later, when writing this piece, I'd written all this out, Harden emailed me back. Jane had been born that morning, and he was a little bit impatient. So Jane, that's your relationship to Richard Feynman. If you ever want to date that talk, just ask Jane. Okay, now, after I left Caltech,
Well, there's a correction to that.
no corrections allowed. We're going on to elephants. I got no time. After I left, I went to MIT, and shortly thereafter, Harden came out to give a talk at Harvard MIT. And he showed we already did that. He showed a slide something like this. Lubert will recognize slides like this, and Chen surely will. This is hemoglobin studies, percent of the sites with occupancy of O2, and some other percentage. We don't even have to know, I didn't even remember. The point is, you have a straight line with slope 1, and other models give curves. And Harden had a curve, and he interpreted it in an elegant way, and it was a great talk. And then some smarmy jerk stood up at the end and said, but is your deviation from linearity statistically significant? Harden looked at him and said, statistics hell. If the data doesn't stand out like the nose on an elephant, I don't use it. What a great response. I contended on some reviews that I got to use that, but I didn't have one. So let me tell you about promotion. I called up Harden early in my career, and I was told to invite him to give a seminar. We chatted, he said, and then very tentatively, how did the promotion go? I just been promoted, I forgot to thank him. So I called, and I said, I'm sorry, I should have told you. Thank you very much, everything went great. Now, Harden could have said many things. Could have said, congratulations, that'd be, conventional. So we know he didn't say that. What he said was, that's great. Means I won't have to write any letters for you for a while. It was years later that I realized that was a very smart remark. But it's also true that he could be the kindest and most generous. So, not long after I started my career, I came back. The last time I was on this campus, it was the late 70s, early 80s, whatever, and I gave a talk. Harden gave me some grief, and I explained to him later that I just was waving an arms, I wasn't sure. But I gave the best answer I could. He said, yeah, I know you were waving your arms. I just wanted to see how you waved. But we talked a little more, and then I'm walking down the hallway on the first floor of Stahl to go to Jim Cohen's lab. And we said goodbye, see you later, whatever. And he said, I really like that stuff that you're doing, which was really nice. He turned around, and I started to turn. Then he turned back and said, what I mean is, I wish I'd done it.
Wow.
There is no higher praise in my life. That was the highest already the peak. So, but what about his style of doing science? And Hayes nailed it. He cheated. But that's a special definition of cheating. Because he assembled, if you will, the answer. He knew the answer before he started working on the problem. It's like parachuting onto the top of a pyramid, a point in space, and building the pyramid below you. So, he interpreted the answer in backfill, is the way I perceive it. And sometimes he didn't. And that I'm going to emphasize. There's a number of spin-offs, papers that were on the list. You've all memorized Steve's list of top publications. Like number 8 is one I'm going to tell you about. So you've all memorized that, so you know all about it. These are papers that he wrote a one-page paper. Never followed it up. And there's hundreds and hundreds and hundreds of papers. And whole fields built on a casual observation. So you've heard all about this one, so I don't have to go into any detail. That's hyperfine to the in-plane hydrogen. But the important point from my perspective is the first paper was a one-page, one-author paper that had that answer, A equals Q to rho. In this case, he did build a pyramid. So he followed it with a 3-page. Oh my God, he was really getting pros. And there was your point. Now he had the answer, now he built some mathematical foundations. And then he built the rest of the mathematical foundation with Don Chestnut, and that's the paper that was signed. Now, that is codified in billions of textbooks, the best still being that one by a former colleague of Harvard. But this is a 2015 paper. Talks about the seminal paper from 50 years ago by McConnell and Chestnut. It's still by name, clear, with all going into the textbook, it's still McConnell who is credited properly with this whole field. My colleague Jim Ivor said the way science is done today, anything published more than 20 years ago, you're free to repeat without attribution. That doesn't apply to Harvard, clearly. So here's another one. This is a spin-off. He was interested in the interaction of spins. It's probably related to the exciton stuff. But here's a molecule with a non-conducting bridge, methylene. And notice again the elegant graphics from McConnell. Hand-drawn alphas and betas and stuff. So he was interested in this problem of the biradical paradox, he called it. He wrote a paper. But along the way, he recognized apparently that it was related to another question. How can an electron on one benzene ring separated by aliphatic methylene groups get to the other side? So in 1961, he published again, one author. It is found that the rate of intermolecular charge transfer decreases exponentially with the length of the chain. He never touched this problem again. And again, March 2015, not long ago. Notice so many more good words. Harden was not so good with good words. I mean, this is hopping versus tunneling, long-range electron transfer, core-thermal oligomers. Graphics are a hell of a lot better, let me tell you. But the McConnell relation predicts that the electron rates are distance dependent and decrease exponentially, blah, blah, blah. A whole field just accidentally, just for the fun. Bob urged me to put this paper in there, or one of them. His relationship to spin densities and spin polarization, he made an observation. If you want to make a ferromagnet, I think I've got a clue on how to do this with organic radicals. Because mostly organic radicals tend to come together, and the electrons on each of the two radicals pair up, and you get anti-ferromagnetic interactions. So he had an insight on how you might get ferromagnetic. Never really found. The search for these magnetism in organic molecules began more than 4 decades ago when McConnell proposed a theoretical framework for the design of ferromagnetic molecules. So, just by spinning off ideas, none of which were his core interests, he created fields. But to me, all of that paled to this paper. I thought then, I read it in the lab. It was the most elegant thing I had ever seen. And I'll give you the whole paper in a minute. And it was a pure spin-off. He never went back. And the arrow that he launched in my direction in 1958 landed like 2 years ago. So, it's Harden, and with a slightly longer story, Harden, Sherlock, and me. So what we are interested in is free rotation versus, this is one piece of what we do, versus Jahn-Teller constraints in non-classical trigonal H2 complex. Because they're trigonal, they are subject to a distortion because they have orbitally degenerate states. And that's all you need to know. That's the Jahn-Teller. H2, according to Greg Kubas, who invented them, is among the most dynamic, complex, and enigmatic topologies, and which is with potential relevance to my own studies of the enzyme nitrogen. So that's why we got into this. So my friend and collaborator, Jonas Peters, who is now at Caltech, had made a complex which had the Jahn-Teller effect, and we were interested in it, and had stoichiometrically an H2 boundary. But the good news to me was that the crystal structure didn't show the H2. So he went to a good technique, Endor, thank you, Alvin, to study it, and that's what we did. So we used Endor spectroscopy to determine what is the nature of the 2 H atoms. It could have been 2 hydrogens. He didn't know. So we used Endor, and what it is, and I maybe didn't do so badly. It's basically an EPR detected analog. You flip a nucleus, and your detector's a little weird. It's an electron spin that's coupled to it. And if you flip the nucleus, the electron says, ouch. And that's how you know you flip the nucleus. And that coupling is a critically important parameter, the A, which you may be able to do. And we get doublet patterns. We'll see that. Yeah, you don't want to know that. That shouldn't have been blurred out, and the point is that everything that I've done in Endor is all Alvin Kwiram's fault. But that's for dinner tonight. So, okay. So, this is the Endor spectra, or some of our Endor spectra, of this H2 complex. We got, and this is the important point, not the actual spectrum. We got signals from both H2 and D2. When they made it with H2, and they made it with D2. But the 2 HDs, the 2 H's of an H2 and the 2 D's of a D2 are magnetically equivalent, yet they give spectra that are off-axis by a small but non-zero real value of 6 degrees. Too little to be 2 hydrides, too much to be an H2 spinning on its axis. So our interpretation was that this so-called Jahn-Teller distortion, it's a pseudo-Jahn-Teller distortion, destabilized the H2 position along one of the 3 bonds. We were undergoing twofold hopping between along this bond and along that bond, and when you average the interactions all in that case, you get some of the kind of blew me away. It was 6 degrees was the number that came out, and I didn't fudge. So that was pretty great. So what the hell? We got a spectrometer, we got some helium, let's do iron. That was our list of coal. So, I didn't show it to you clearly, but we got this beautiful indoor spectrum from the H2 complex of the iron. But we didn't get in. We were doing Alvin's experiment. We were getting anything. We were getting zip for the H2 complex of cobalt. Now, that afternoon, the experiment was being run. I had to go take a daughter to the dentist or something. Coming back that afternoon, a graduate student, Bill Gunderson and George Cutsale, then postdoc Bill, then graduate student George, were doing the experiment, and George was going out to do something. And he was crestfallen, because they weren't getting any spectrum. This is what they were getting. But I read McConnell's paper from 50 years ago, and I got incredible. I was in like the 5th vibrational state, floating somewhere above the ground. The first paper on the subject was written about Sherlock Holmes. Silver Blaze is a horse that got stolen. Is there any point that, the stupid cop at Sherlock in which you wish to draw my attention to the curious incident of the dog in the night? But the dog did nothing in the night. And as Sherlock explained, the absence of a signal provides the solution to the problem. And Harden knew that, but I don't know whether he read Sherlock. Maybe so. So whether he cribbed it from Sherlock, I don't know. But he knew it in 1958. And I remembered the paper because of its elegance. And here's the paper now. This is a paper, he had nothing to do with this problem. Realistically, shouldn't. It's essentially a half of a page in J. Chem Phys. The problem was suggested to him by his Norman Davison, who not suggested the problem, but noted some very smart folks had done some EPR spectra with some funny results, and they reported their funny results. And Harden, just by the way, figured it out. It had to do with the fact that the overall function, the Pauli principle, applied to the molecule, which is an NH2 radical in an argon matrix at 4 Kelvin, that it was rotating, that introduced an implication from the Pauli exclusion principle, and just applying the fact, the elegant application of the fact that the overall function, wave function, must be antisymmetric for the two fermions of the H2 as they rotate, was enough to teach him how to interpret the spectra, EPR spectra of these guys. Well, that's what happens to us. The old total wave function, this is from our paper, for two identical fermions must be antisymmetric with respect to exchanging the particle. The absence of the H2 spectrum requires that we have a free rotor. And I didn't show it to you, I took the slide out just this morning. We get the deuteron indoor just fine, which you should, applying the Pauli principle to the deuterons, which are bosons, predicts indoor and we see. And then, best of all, HD has no exclusion principle constraints. And you see both the H indoor and the D indoor. And it all came from Harden's. I won't say came from, but it was like he was talking to me from a half a century before. So I love this paper better than many, maybe all, because on the first page I could talk about the latter being corollaries to McConnell's recognition of the role of these quantum statistical considerations in paramagnetic resonance spectroscopies, and that's to the paper, the 58 paper. And then I had the opportunity to add this acknowledgement. Work is dedicated to Professor Harden McConnell's recognition of the role of these quantum statistical considerations. Paramagnetic resonance spectroscopy occupies but a small place among his numerous scientific contributions on the occasion of his 87th birthday, and I thank you guys for giving me a chance to show this.
So I apologize for keeping you from your coffee, but I have a plane to catch and there's no alternative. Actually, having listened to the wonderful talks that have gone before, I would rather just sit and listen and get up and speak myself. But in any event, I will tell you briefly about my own experience. And it really begins in 50 years ago when I joined the McConnell Lab, which at the time was populated by those listed here. And especially I would call attention to the names of Seiji Ozawa, Murano Gata, and the Horowitz, who were studying an aspect of the oxygenation of hemoglobin and the conformational change associated, and Wayne Hubbell, Philippe Pivot, Dr. Celia Carl Scandella, who were interested in membrane structure, which was the problem which I studied as well. I should say that when I arrived at that time, I went to Harden and told him he was the chosen person. I was going to join his lab, and he told me, no, that wouldn't be possible. And I asked him why. He said he didn't want to have my father looking over his shoulder. But then I explained to him that I had interviewed other possible candidates for the job. I had interviewed Bruno Zim in San Diego. I had talked to Paul Flory. And I had specifically come to Stanford Chemistry to work with Harden McConnell. He said, in that case, fine. He said, write a research proposal. So I talked to people in the lab like Wayne and found out what were the interests. And I learned that McConnell had two particular interests that I had just mentioned. One, the conformational change of hemoglobin. So the mechanism at the basis of allosterity was one of the major issues in biophysics, biophysical chemistry at the time. And the other, membrane structure, also one of the major challenges. At the time, hard for most people here to believe that the structure of membranes was not known and object of debate, but I'll shortly explain very briefly why that was the case. What Wayne and others also told me was that the transition that had been made in the McConnell group from especially theoretical work and physical chemistry to an interest in biophysics and biology was partly a consequence of the synthesis by Rosenson of the nitroxides, now called a spin label, and in particular the molecule which Wayne actually named tempo. And I'll come back to that in a moment. So I knew that I was in the right place. I had been indeed looking for the purpose of graduate work for someone who was a world-class physical chemist, but with a serious interest in biology and wanting to solve the pressing problems of the time. And I think Harden was almost unique in that way. And I'll come back again to that later. I began my work by painting my lab bench. Finding a centrifuge. There were none in the McConnell lab. There happened to be one in the basement of the old chemistry building, and I found out that we could bring it up and get it working. And then all the rest of what Wayne and Seiji and the rest of us did was really had improvisation, because the lab wasn't equipped to do anything in any way related to chemistry or what have you. The research proposal I wrote for Harden was, in retrospect, foolish, but it was, to him and me at the time, both of us novices in the subject, perfectly reasonable. So I wanted to apply magnetic resonance to a pressing problem in membrane biology, and regardless of what was the solution to the problem of the structure of membranes, there was the issue of how ions were transported from one side to the other, and that was central to everything in biology, neurobiology, and what have you. And so I proposed that we would use magnetic resonance to measure the rotation of a protein in the membrane that would carry an ion from one side to the other. Even from the work I later did, we understood eventually that was a stupid idea. But as I say, that's where I began, and I chose a very abundant ion transporter, the calcium ATPase sarcoplasmic particles. This is the molecule responsible, the enzyme responsible for triggering muscle contraction. And I set about isolating and fact, worked terribly hard. I worked a full 16-hour day, 7 days a week, 365 days a year for 3 years, and had nothing to show for my efforts. And Harden appreciated how hard I was trying, and he was sympathetic. He said to me one day, he said, you know, if this were a differential equation, I know a lot of tricks. But unfortunately, I couldn't solve the problem. And late one night, when I think Wayne and I were washing glassware in the library about 3 in the morning, it occurred to me I could tackle a much simpler problem. And I'll come to that in a moment. But I need first to explain about membrane structure. So, as I said, it was an unsolved problem. On the one hand, there was the idea dating back to 1925 that the structure of membranes is based on a phospholipid bilayer. Two monolayers of lipid molecules oppositely oriented with the inside and outside living cell, so the aqueous solution on either side, and a hydrophobic barrier in between. The alternative, which was popular at the time, and especially popularized by David Green and by John Singer, was so-called proteolipid hypothesis. And it supposed that there were subunits of proteins and associated lipid molecules that were organized in some manner to form lipid membranes. Now, again, slightly out of chronological order for my story, about halfway through my graduate work, a paper appeared by the same John Singer proposing the so-called fluid mosaic model of membrane structure. McConnell came into the lab that day. Wayne will remember this, and in typical, very brief, laconic fashion, he said, "What's new?" We and others, over the course of those 2 to 3 years, from the beginning of my graduate work to the time of the publication of this paper, had all come to realize, and indeed those working in the subject collectively understood, as shown in this diagram. The structure of membranes is based on a lipid bilayer with protein molecules dissolved in lipid solution, a principle which engaged Harden's interest for all the rest of his career. So understanding then that the lipid bilayer was really the solution to the problem, as I say, I realized late one night or early one morning an alternative to my futile attempt to study the rotation of proteins in membranes. It was to study the rotation of a lipid molecule in a membrane. To ask the question, which had not been done before, does a phospholipid ever pass from one side to the other? And I refer to this as flip-flop because I had been studying with a phenomenon called flip-flop in electrical circuits as an undergraduate with none other than Ed Purcell, who was one of the inventors of nuclear resonance. And I was actually very unsuccessful in that course with Ed Purcell, but I did remember about flip-flop, and I thought it was an apt term, and wanted to measure the rate. And for this, I'm very much indebted to Wayne Hubbell. Wayne may or may not remember that he had synthesized a molecule that he called tempo-choline. And he donated that synthesis to my work. And I wanted then to couple it to a phospholipid molecule. These are the hydrocarbon chains. These are actually formic acid chains, C16 chains. Saturated, and that is important for the purpose of this analysis. Well, I was unable to synthesize the lipid following the literature, and so Harden allowed me to travel to Utrecht in the Netherlands, where in the laboratory of Lawrence van Nemen, who was really the dean of the world's expert in lipid synthetic chemistry at the time, I learned how to do this. Brought back what I had learned, and I think it was helpful to Wayne and others afterwards. As Wayne would tell me, I incorporated this lipid molecule in vesicles drawn to the shape I don't have time to explain, but very small, about 500 angstroms in dimension. And what is symbolized here by the black dots are the spin-labeled little molecules in a sea of otherwise agiolesic molecules, so not paradigmatic molecules. And I eventually discovered a trick which was to erase the spin label or the paramagnetic signal from the outside by the addition of a reducing agent at 0 degrees, at which temperature it could not penetrate, leaving only the molecules that were on the inside. And then I would warmly sample up, allow flip-flop to take place, and then erase again and measure the decrease in the paramagnetic resonance signal. And I arrived at the result which is shown here. A decrease, this is a semi-low plot, I could measure the first order rate of this process, and the important point took place over a time of many hours. And this was something I think unexpected given the short distance, only the dimensions of a single molecule for the path of diffusion from one side to the other. I completed the work and I wrote a paper. In those days it took me months to write a paper, sometimes days to write a sentence. I brought the paper to McConnell, expected him to criticize and make a lot of changes. He didn't change a word. Instead, what he did was to look at me and say, "Is it true?" And I have told every student and postdoc who worked with me ever since how important that was. And it really relates to what you've heard from others. It was about this matter of intuition. It wasn't really important what I wrote, how I wrote the paper. It wasn't important about how I prepared the figures. What mattered was whether we were sure we were right before we published. And that was something you could know not only from the work you had done, but what was most important, from a sense which is difficult to describe, that people refer to as intuition, of whether this is likely to be right or not. And I often thought of how one can tell whether you got it right or wrong, because there is a ring of truth to a correct result. So, this was McConnell's dictum, and as I say, it's one of many things that he said which has stayed with me ever since. I told Steve that I thought it would be nice in talking about work done with him at that time to try and indicate briefly what was the trajectory of work in the field since. And Brian Hoffman has known that so well, and so the others. And so I'll say very briefly what was, in a way, an embarrassment to me about what followed on what I had just described. Something very nice, which I should have thought of, but I didn't. I can't blame Harden. It's really my fault. Only a year later, Mark Brecher wrote an article called Some Principles of Biological Membrane Structure, in which he pointed out our result showing that lipids did not pass at a meaningful rate from one side of a lipid bilayer to the other had an obvious implication. Because we know that membranes are asymmetric in nature and they have different lipids on one side than the other. There must be a mechanism to transport from one side to the other. And so Mark coined the term flipase for an enzyme that would catalyze that process. And then Philippe Dubois, who you may recall from that list or from target practice that you saw him making of Harden in one of the earlier slides, was the first to actually discover flipase. And after that time, many have been found. And here's our list, which I discovered when I was looking last night. A very long list. These molecules are called P4 ATPases. HS is Homo sapiens. These are the evolutionary trees for many of the molecules. They're very abundant in nature. And as I say, I missed the boat. I really should have immediately realized that such molecules exist and gone on to discover them. But instead, I was influenced, or I should say really hard influenced, by work done by another person in the lab at the time, named Hoffman Saley. And this you don't have to read, but it simply draws your attention to a paper he published during the period when I was doing the work I just described. And what is important about this paper, one day, Harden was leaving the lab, as he always did, at a very precise time to go home for dinner, carrying the book you saw on a previous slide from Brian Hoffman, Carrington and McConnell. And I knew that Harden admired that book, and that if I wanted to understand nuclear resonance, I should study the book. But Betty Gaffney, seeing him carrying the book home, said, "What are you doing with that?" I mean, obviously he knew everything in the book. And he said, "I'm going to read the book tonight." He said, "Joe, as we call it, Seeley, knows something I don't know." And he went away and absorbed what was the essence of what is described in this paper, which was the determination of an order parameter for a flexible molecule, which here Seeley applied the problem of a membrane model, and then which Hubbell and Arun did to great effect and very beautiful work, which followed, which I think was probably the content of the most cited paper on that list, which we saw in the first slide. And of course, Wayne will talk about that later. So what Arun took from this was something important about the fluidity of the lipid layer. And he appreciated that in addition to the measurement of flip-flop that I've made, it was important to ask the other question, not only about diffusion from one side to the other, but diffusion within the plane of one molecule. And he pointed out to me that could easily be investigated by measuring the line broadening of a nuclear resonance line by a spin level in the molecule. And so, following his suggestion, I performed that experiment. What Harden really liked about this was not the result, which I'll show you in a moment, which was important and stood the test of time. He liked the problem that I encountered in the way I eventually overcame the problem. When we doped lipid layers with very small amounts of nitroxide spin levels, those very small quantities would rapidly disappear. They were consumed by a process of oxidation of the lipids radicals generated in the lipid layer, which then consumed the nitroxide radicals. And eventually I resorted to the synthesis of a molecule called dihydrosterculic acid, which has got a 3-membered ring in the middle of the hydrocarbon chain. And Harden just thought that was terrific. He liked the word dihydrosterculic acid, and he would always remind me. The result was, as he anticipated, line broadening. This is these are protons of the 3-methyl groups of the choline-moiety of the phosphatidylcholine molecule. And you can see line broadening in the presence, and then after that, in order to calculate what would be the case in the absence of lateral diffusion, I derived an expression for that in the absence of lateral diffusion, and that's plotted here. And the evidence is unequivocal that lateral diffusion takes place, and from the further measurements I won't have time to explain, we can place a lower estimate on the frequency with which a molecule on one side exchanges or changes positions with one on the other at least 10 to the 4th times per second. Now, as I mentioned, Philippe Deveau joined the group during this period, and he undertook to measure the actual value rather than the limiting one that I had obtained. And he did it by an experiment of a very straightforward design. He placed the driver patch of the same spin length of phospholipid that I showed you onto the middle of a cover slip, some slide, and then he laid down some unlabeled lipid on the other side. He allowed these two to hydrate. He pressed the two slides together so that he had a spotted labeled molecule in the middle, and then he measured the change in the line broadening of the paramagnetic resonance spectrum over time. And he and Harden came to the conclusion that in fact the frequency of exchange between the two sides was exactly an order of 10 to the 7th per second, corresponding to the diffusion concept of about 10 to the 1 centimeters squared per second. And I must say, I didn't really believe that experiment. I thought it was not convincing because I didn't see why I should accept that one patch of lipid got properly absorbed in the bilayer on the other side. But they proved to be correct. And later on, when a measurement was made by fluorescence recovery from photobleaching, a number almost exactly the same as Gill and McConnell had derived and so this was a verification of the result, and contrary to my skepticism, they were correct. Now, it was an interest in this aspect of the lipid solution which occupied Harden's attention for much of the rest of his career. He was absolutely fascinated by the characteristics of this two-dimensional solution, and he and Arun, Radhakrishnan, who will speak later, performed beautiful studies, both experimental and theoretical, and we'll hear about that later. One might wonder, and I often ask myself, why did Harden not gain greater recognition within the community of biologists for his interest in membrane structure? And I think the answer is on this slide, which relates to which we heard from someone, can't recall which of the presentations earlier, in which you heard about a paper that Harden wrote about ferromagnetism, in the case relating to paramagnetic molecule. But here he writes about understanding membranes, which is something all biologists may do. And then he explains that the intensity fluctuations in blebs and membranes are those expected for theoretical 2D icing ferromagnet, and no wonder biologists really caught on to this enthusiasm. So, I wanted to just say something in conclusion about the impact that Harden had on me, as you have heard on many others. And I thought of two ways to do that. One, to tell you about something Henry Taube once said. Henry, as you know, was a great inorganic chemist. Very knowledgeable and respected. Henry once told me that if he had a question about chemistry, he would go to Harden. And that Harden would always say the same thing. He would say, well, do you want a physical explanation or do you want the mathematical? And of course, Harden always knew the explanation. And the other way to convey what I would like to do is just in a line. It was the first line of the acknowledgement of my graduate thesis, where I wrote the best, the smartest thing that I did in this work was to choose Harden McConnell as an advisor. Thank you.
And Mark both gave you a very nice, thorough view of McConnell's philosophy and science and how he thought about things. And I agree wholeheartedly with everything that says. I won't repeat all of those things. I'm going to go in a slightly different direction and focus on McConnell. Instead of one topic and that's a spin it. But there is one thing that I should say about the philosophy of that lab at that time they didn't mention, and maybe they did obliquely. But the one thing I got out of doing science there more than anything was the motivation. It was just because it was a hell of a lot of fun. You weren't thinking about getting a number of papers, you weren't thinking about how to get promoted, you were just doing it because it was a hell of a lot of fun. And that was a major thing that I came with. But anyway, now on to this. So I arrived at Stanford in 1965 as a new graduate student, and that turns out to be the year that McConnell presented to the world in this paper the idea of using stimulators to investigate biological molecules. And I was very interested in biology at the time, and I wanted to join his group, be part of that effort. But I was warned away by lots of other students. Look, this is a tough topic. You don't want to work with them. It's hard on graduate students. Why don't you find somebody easier to work with? But, you know, despite those warnings, I enjoyed this lab. And over the next few years, I got to know him very, very well. I could tell you hours of McConnell stories. In fact, we had a couple together raising goats. That's the most interesting story. Don't tell me about that one. But I do want to tell you one story that tells you what kind of a guy McConnell really was. And the story starts with the first paper I ever published together with him. This paper here. And Roger already alluded to this later. This is in 1968. And at that time, we were trying to see what we could learn about membranes and spindles. And at that time, there was very little known about membrane structure. It was known there were phospholipids in a bilayer configuration probably, but nothing else was there about where the proteins are and what the state of the hydrocarbon chains were. Very little was known about it. So McConnell and I were trying to see what we could find. And we had this small molecule here, which was named tempo, and we put it into suspensions of isolated natural membranes, nerve, fiber membranes, muscle membranes, and pure phospholipid vesicles. And what we saw was this spectrum here that had two distinct components to it. The interpretation was, and what was suggested, was that this small molecule was partitioning from water into some fluid hydrophobic phase. Now the key word there is fluid hydrophobic phase. From this we ended up concluding that the interior biological membrane must be liquid. Now we all know that's true now, but at that time it wasn't generally appreciated. In fact, it was considered heretical by some people that it was fluid-like rather than a wax-like solid because it changed the form. Now probably because of the result of this experiment, McConnell was invited to a very important Gordon conference on energy coupling mechanisms in 1968. And so he came into the lab and said, Hubbell, I want you to go to this meeting with me. So I was greatly honored, of course, to go to the meeting with him. And he picked me up, and on the way to the airport, he said, Hubbell, do you have a tie? And I said, no. And so he stopped and he bought me a tie. I later found out why. So we get on the airplane. Now, I remember I was a really new graduate student. Never been to a meeting in my life before, never given a talk. But on the plane, McConnell looks at me and says, Hubbell, he said, you should give this talk. This is going to work. So he saw the panic in my face, and we compromised. He said, okay, look, we'll do it Mutt and Jeff style. I'll give the first half of the talk. And we introduce stuff, and you just get up and show your data. And I have all the transparencies made, and some people are old enough to remember transparency. So we agreed we would do the Mutt and Jeff thing. So we get to the meeting, and that's what happens. And we talk, and there's some traumatic parts of it that we can talk about some other time. Here's a picture from that Gordon conference. And there's some very famous people at this meeting. This up here is Walter Stokenius, who discovered bacterial rhodopsin and described its properties, the great Britain Chance, Paul Boyer, Brian Racker, a guy named John Singer, we'll talk about more in just a second. A lot of important people at this meeting. I was giving this talk, and we presented this thing. So if you focus here in the corner, there are two people out of this whole mess that have ties. There's McConnell, and that's me. This is a very casual meeting, but we had time. I had to have the time because I was going to give a talk. Anyway, this is John Singer. Now, John Singer, at that meeting, fought against us. We said, no, biological membrane system can't be fluid for all kinds of mechanical reasons and whatever. He argued vigorously against the idea. But nonetheless, a couple of years after that, he published this famous paper called The Fluid Mosaic. So he clearly came away from that meeting with some ideas. And this really annoyed McConnell justified. Anyway, he knew that they were fluid, and I knew that they were fluid. Anyway, so when we got back to Stanford, we continued to work on to find out what we could learn about membranes and spin labels. And I bring this paper up because it was highlighted as probably in McConnell's illustrious career. This is the paper that has the most citations of any of his. It's a very important paper. And my contribution to it is synthesis. I actually contributed to this by synthesizing a series of phospholipids in which the nitroxide was moved up and down the chain at various positions. And I wasn't an organic chemist. I got some help from Jim Trudell, who was a student of Carl DeRoss's at the time, and was patient enough to show me how to do granular reactivity. So we made this series of spin labels and put them into biolayers, and we got a characteristic line shape from them, which McConnell immediately recognized as due to some anisotropic motion as these molecules spin about their long axis and superimposed on them with fluctuations in the hydrocarbon chains. But he derived an elegant theory to account for the relationship of the spectrum to the motion of these molecules. And as a result of that theory, we were able to compute order parameters as a function of position of this nitroxide up and down the chain. And that gave a quantitative description and discovery of the fluidity gradient in biological membrane, which had an enormous impact on the field. In fact, the models described in this work are still used today by many groups who investigate the effect of drugs and proteins and so forth on the properties of biolayer. So a very important thing. Now, at the same time, this gives you an idea of the diversity of this lab and the excitement. At the same time in the lab, my lab mates, Seiji Ogawa and McConnell, were exploring essentially an orthogonal direction. What did you learn about proteins from spinning? And the protein they were working on was hemoglobin, shown down here in the picture. The hemoglobin was very much in the news at that time because of its cooperative behavior. Everybody wanted to understand the cooperativity. So it turns out nature serendipitously provided two cysteine residues in this molecule that would be used to attach spin layers, which they did. But even more remarkably, these happen to be exactly in the right place in the molecule to sense changes in the structure of the protein with oxygenation level. So Seiji was able then to look at changes in structure. These are the EPR spectra showing the changes, the details are important. To me, this was really inspirational because it showed you could use spin labels to investigate the conformations of proteins in solution to try to understand how they function. They learned a lot about cooperativity from this work. So now I'm going to fast forward 50 years at the present time when technology has advanced enough that you could put a spin label not just in places where nature provided systems, but you could put them anywhere, at any protein, so you could put spin labels throughout. So I want to tell you a little bit about, in the context of these advances, what spin labeling has come to, essentially what has grown from the seed that McConnell planted here. This is a huge field of spin labeling has become. Now I'm going to tell you just one small direction that it's taken. I picked this one because it's one that I know McConnell was excited about in my communications with him over the last few years. All right, so we'll start at this point. So the thing that made this spin labeling and the ability to do Seiji Ogawa's kind of experiment possible with any proteins generalized that happened in the 80s with the invention of sort of site-directed mutagenesis, where you could take a given amino acid, mutate it to cysteine, where we can put a spin label, and then react that with a highly selective nitroxide reagent that would introduce a spin label into the protein. So now we can put it anywhere. So where do you put it? How do you make that decision? Well, the other important thing that came along was a huge database of protein crystal structures, including membrane proteins. So these gave a starting point for rational design of where to put the spin label to test specific ideas. Well, so you could say that once you have a crystal structure, why do you need spin labels at all? Once you know everything, structure. And as people that are in this field now know, that's certainly not the case. In the crystal, the lattice forces trap and confine the protein to a particular conformation. But in solution, they occupy a manifold of different conformational substates and are fluctuating back and forth on some time scale. And this turns out to be crucial for their function. And sort of an energy landscape view is shown here with this picture. So this is a free energy surface of a protein in solution. This is a cartoon from Gill. And in this representation, the free energy, internal free energy of the protein increases in this direction. And in this representation, the other dimensions are such that the width of this funnel-shaped surface represents configurational entropy. So way down here at the bottom is the native state of the protein, the most ordered, the lowest configurational entropy, the lowest energy. And this is what you see in the crystal structure. But then if you go up this scale a little bit, you find that a little bit of energy above, we'll call it excited state, it's above that ground state. There are a manifold of conformational substates. And the protein's hopping back and forth, exploring conformational substate on some time scale, which we'll talk about in a minute. Now, it turns out this is important functionally. This model, which has been confirmed in a number of cases now, provides an explanation for the promiscuity of protein-protein interactions. A single protein can interact at the same surface with multiple partners. And maybe it's because each one of these conformations is really a different protein in terms of these interactions. There are many other things, but that's just one point. Now, as you evolve even higher in energy, up here, the most disordered highest energy is completely unfolded form of protein. So without any further explanation, I'll just make the point that if you want to know how a protein works, for a particular protein, you have to find out some details of the energy landscape of that protein solution, the existence of these substrates and so forth. So the challenges, experimental challenges, are first, we have to have some way of determining the existence of these substrates in the first place. And then what is their relative population solution? Well, for the relative populations, you get free energy. So that's sort of adding an energy landscape to your an energy scale to your landscape. And then, of course, you have to determine what are the structural changes that involve. When these molecules move from here to one of these excited states, what's the magnitude? I mean, is it a whole molecule is changing shape or just a tiny movement of one part or something? That's sort of adding a length scale to this free energy surface, to this landscape. And then finally, there's the time scale. Time scale is very important because a protein has to stick around long enough to do something. And right now it's believed that these conformational fluctuations between substates is on the order of microseconds to milliseconds. So that's our initial time scale that we start looking at. So the main point I want to make today is that McConnell spin labels in this sort of modern context is up to this challenge. And looks very promising to be able to determine every one of these things, to add all these scales to the landscape in a way that no other technology can. So I'll just give you a quick, brief overview of how this is probably going to be done, and likely to be done. Many of it has already been demonstrated, but without any details, just to give you an idea of how these things go. So I'll consider these in order very quickly. So how do we get an energy scale, and how do we detect the presence of multiple substates? Well, this is sort of built directly on the McConnell experiment. Let's consider we have a protein in two conformational states flickering back and forth. So the idea is that we'll engineer a spin label based on a crystal structure now. We'll engineer a spin label at a site where it experiences different environments in the two conformations. So in general then, the UPR spectra of this spin label, it's not important what these line shapes mean right now, but just it is important that they're different, they're distinguishable. Now what is important is that this fluctuation time of microseconds to milliseconds is slow on the EPR time scale. This is very important because what it means is there'll be no spectral averaging effects at all. So what you see in the equilibrium mixture, if it's flickering back and forth, is a two-component spectrum, which is simply the algebraic sum of the two components in proportion to the amount of those states that's there. Very simple. In fact, in a real experiment, how we conduct this is that we choose a site from the crystal structure that we know there should only be one state, and those are usually on the surface of the protein, and then we scan the nitroxide mutagenically through, looking for the appearance of these two component spectra. And the result is a map of the regions of the protein that are undergoing conformational exchange. It's just like what Seiji McConnell did, but now we're not restricted to a particular site anymore. We can explore the whole molecule. And of course, by spectral analysis, you can extract populations, therefore get the free energy of the state. So that's how we get an energy scale to the landscape. And this actually works. It's a little bit more complex than I'm presenting, but in fact, so the other question is, how do you get a length scale in? This tells you nothing about how big the changes are. This says they're different. But you really need to know the structure of these other states. So the approach to that is by distance measurement, again, with spin labels. So I'll just describe quickly to you this experiment called here, double electron-electron resonance. It's a method for measuring distance. And you engineer for the protein two spin labels like I'm showing here. This is myoglobin. This is one of the few proteins that's so rigid the crystal structure is about the same solution. It's a very rigid protein. Now, in this Gill experiment, you deliver a pulse of radiation to one of these spins and you observe it with a classic Hahn spin echo. And the detail talk is important here. And while you're doing that, you tickle the other spin. with another pulse of various timing. And what you see in the echo is an oscillatory behavior, and details aren't critical here, but it is important you can fit this data to a probability distance distribution. So this is real data for this protein. You can see the distribution is very sharp and narrow, and the position of it is exactly where you get from calculating the crystal structure. So that's a very powerful technology. But the real power is shown in this next image. Here's another protein that we're studying. It's a lysozyme molecule that's a mutant that generates a cavity that binds ligands. And the crystal structure of this mutant is identical to the wild. But in solution, the story is very different. So this is data for a pair of spins that is frosted domain in this molecule. And what you clearly see is two discrete populations that are existing in solution at the same time. We're directly looking at the two states that are fluctuating back and forth. And this gives us a length scale. These peaks are 5 angstroms apart. And this protein, this domain, is opening and closing at the movement of 5 angstroms. So you could imagine with a sufficiently large number of pairs, you could map out the whole structure. And those kinds of experiments can be done. And the distance range here is just perfect for looking at proteins. But now, so we get a length scale and energy scale. This is this sort of principle. I want to go back to measuring or detecting the existence of conformational substates. And I mentioned it's not quite as simple as I showed you, and it's not. There's a caveat. And explain here. Let's suppose that I want to see if there's some excited states present in a given protein, and put a spin label in there. And what if the problem is that this excited state is of sufficiently high energy compared to the ground state, that it's in very low populations? No, I'm not just setting up a straw man. It turns out that's the usual situation. These excited states are a couple of kilocalories above the ground, which is a 2 or 3% population. You'd never be able to pick it up in the CWEPR spectrum. It's just a minor state. So what do you do about that? Because that's a very important problem. So the solution was presented, and this is right up to the present time when we're talking about. The solution was presented by a guy named Akasaka and his colleague Keller. Which they showed with NMR convincingly, and there's still some discussion about this, but the application of pressure to a conformational equilibrium cleanly shifts the population from the ground state to the excited state. Which implies that these equilibrium constants are pressure dependent, and they are, and it's because the partial molar volume, believe it or not, of the native state is the largest in a non-solid, not the excluded volume, but the thermodynamic partial molar volume. And we could discuss why that is later, but the important point is that's the case, it's true. So this is fabulous, right? Because it means it was just using pressure modulation, we can titrate up this landscape. We can isolate specific states and so forth. So in the last few years, we've constructed a high-pressure EPR spectrometer and used spin labeled proteins, and to the extent they can be compared, we confirm Akasaka's idea. But I have to tell you that there's a great advantage to the EPR on time scale. In the NMR experiments, when you put them under high pressure, the proteins, and they go into these excited states, the exchange rate is just right to average the relaxation effects that you lose the data. They get so broad you can't see it. But in EPR, you see everything. And what you see is a beautiful transitions to discrete states that you can titrate with pressure. So this becomes a very powerful part of the tool then that allows full access to the energy landscape in terms of population. Now, the last point I'll make is, so how do you get a time scale? This is really important, and can you get a time scale? Because all of these rates, like microseconds, milliseconds, are way out of the EPR intrinsic time scale rates. How would we do it? So this slide already suggests one experiment, which I like very much, and McConnell liked a lot too. And the idea is, since these are pressure-dependent equilibrium, if I have an equilibrium state sitting there and I jump the pressure to a new value, fast compared to the exchange rate of the protein, the system will be initially out of equilibrium, relax back to a new equilibrium state, and from that relaxation dynamics we can extract. It turns out this works, and we built a pressure jump spectrometer that is fairly low resolution in time, but good enough for some things. I'll just show you quite briefly the kind of experiment one does. So here's this protein native hemoglobin, exists in equilibrium with an excited state that's really well known, really well characterized, only one of the level of distance. At atmospheric pressure, this thing is about 100%, it's 98% populated. And you can populate the excited state with pressure to about 98% at 4 kilobars, 60,000 psi. Pretty low pressure in physical world. Now, that's how we got these EPR spectra. So we can monitor these two states by putting a spin label at some point that it senses difference in these structures. And it turns out site 54 is one of those sites. And what you see here is the EPR spectrum, now a Q-band, actually using Hayes-Griffith's Q-band bridge, which he gave to me several years ago. The reason for using Q-band is subtle here, but these are Q-band EPR spectra. You see they're quite different. Monitoring the population of these two states. So this equilibrium, of course, should be pressure dependent. And as you change the pressure, this equilibrium will shift back and forth. And it's easy to monitor simply by following the intensity of the sharp field going here. So you just set the spectrometer in one position, jump the pressure, and watch what happens. And it actually works. This is a fairly slow transition. We're jumping from 500 bar to a kilobar. And so we're shoving the equilibrium towards this multi-globule state, and it's being populated. The time scale of this is about 500 milliseconds. It's slow for all kinds of interesting reasons. And things will, but it's well within the normal range of protein-protein population exchange. So this is just the first experiment. This is sort of, these things are sort of underway with the current graduate students. So we can measure relaxation kinetics in this time domain, and knowing equilibrium constants in this rate, we can extract individual rate constants and therefore lifetime. So this gives us a tool to explore, using a high sensitivity VPR to explore this time domain, which is even harder, in some cases, very more. So while we're on the subject of time scale, I'll just finish by pointing out to you what I think is possible and where we are. So this bar represents the full time domain of protein motions that you might want to study. And what we've been talking about is conformational exchange that occurs in this sort of long time domain. It goes way out beyond the second in this range. And so P-jump, this pressure jump technology, is clearly able to monitor pressure jumps in the millisecond range. I didn't mention it on the other slide, but the pressure jump time is about, with our current instruments, about a millisecond. But we're pretty sure that we can do 10 microseconds with the piezoelectric drivers, so we'll probably extend that range a bit. But for slower things down here, microseconds, it turns out there is a magnetization transfer experiment, pulse saturation recovery, that does measure exchange rates in this time domain. In this experiment, you apply a saturating radiation pulse to the spin label and watch the signal recover, and the analysis can give you exchange rates that are on that time between the two states. And finally, way down here, proteins also have spectral density way down here in the nanosecond range due to fluctuations of the backbone. And conveniently, that is the time domain that affects EPR spectra, as we showed early on. And so from simple analysis of the spectra, you get this information about the modes in this range. So the point is that it looks like this simple spin label in proteins has access to this full dynamic range of measurement. I believe this is going to will become a very routine measurement at some point pretty soon. And so they're very, very powerful. So just to summarize what I started out with saying that, okay, proteins, everybody believes now, and this seems to be true, that we have these complex landscapes, and for a particular protein, these are the features you really want to find out. The energy scale, which I showed you could get from analysis of these two components, spectra using pressure modulation, and from here gives you the length scale, and then what we just discussed, you have a time scale associated with it. So some of these measurements, like the distance, absolutely unique to the EPR, spin label and stuff. There's really no access any other way to this kind of data. Long range distances with resolution of specific subsets of these. So spin labeling has is what come from the seeds that McConnell planted, and it's still growing. And I'll finish by showing you this slide, which I just did on the way here. Actually, we looked at just literature search on things that say spin labeling, starting at about 1970 or something back here. It's an exponential rise. This is an exponential fit here. So this technology is certainly not peaked. It's got a long way to go. I showed you just one direction that it's taken to look at protein dynamics, and something that intrinsically interests me a lot. But there are many, many other directions that people in this audience have taken that account for this pretty rapidly. So, I mean, I've spent my entire career working on what McConnell started. So I owe him a lot and feel those him a lot. So, boss, wherever you are, thank you, and thank you for listening.
I just want to say one thing about citations that you might find amusing. So Lyle, a PhD advisor, wrote a paper that referred to McConnell's work on superexchange. We heard a little mention of it early today, and they made a mistake. They misspelled the name. They left off one L. And there are hundreds of papers citing McConnell with one L. Okay? People who never read, of course, the original paper. So that's what you could. Okay, so there's a question.
Yes, this is wonderful, and I'm just curious, what do we know about any effects that the spin label itself might have on the shape or the length or the dynamics of the protein, that maybe hanging the spin label on it makes it clumsier or something?
Yeah. No, that's a very important, interesting question, and NIH kept hammering on me in the early days over and over and over, and so we were very sensitive to it. It's absolutely remarkable that I just showed one example of the spin label, but that particular spin label is really important. This methane thiosulfonate reaction product. It turns out that on the outer surface of the protein, it does absolutely nothing. Very minor effects to the function or the structure. But we have crystal structures, probably now that we did in my lab, of maybe more than 20 proteins with the spin label that certainly aren't modified. And we showed a solution using these other methods that it doesn't modify the conformation. But absolutely remarkable, even at buried sites in the protein where you really expect some bad stuff to happen. This little spin label has internal energies that are low enough that it can repack and sort of get out of the way and still allow just local distortions and still report the news rather than make the news. So that's been investigated, and it has to be evaluated in particular cases. They're very unstable proteins that if you have an equilibrium between multiple conformations, say where they have about the same internal energy, then that can be changed by interactions in the local environments. It's very sensitive there, and the interaction energy we estimate is on the order of a few tenths of a kilocalorie. It's enough to shift things around, but not change the story. So they're very great things.
If I can take the liberty, so when I was a graduate student, Professor Harden McConnell came to give a seminar, and some of us were asked to meet with him for an hour, and we sat there in dead silence. And I raised my hand. He was already my hero. I raised my hand and I said, well, this spin label stuff that you've been doing, these spin labels, your question. I said, this has got, especially Hubbell's work, putting these things in membranes, this has got to make a huge difference. How about these beautiful deuterium quadrupole resonance experiments that certain other people were doing? And McConnell looked at me and said, who are you? That was it.
There's one more thing to add. Brian told me a story about the people in seminar where McConnell made the comment that if data doesn't stand out with the nose on an elephant's face, I don't use it. And then he looked at the audience and he said something else at the end. He said, now, are there any intelligent questions?
Well, thanks very much, Steve. It's a great honor, of course, to be the only non-student at Harvard. to be allowed to speak, and maybe have something to do with being a grad student at Caltech. But maybe more to do. I do claim some dissent because Norman Davidson was a very important mentor of mine at Caltech, and we were trying to figure out some things about kind of DNA And then I came, the first time I met Harden was when I was coming out for an interview at Stanford. And I remember it was a kind of a strange thing, and he had this bandage on his hand in 1981, or 2, and he just casually mentioned it was a gunshot wound. I didn't want to go there. I thought, okay, let's not find out anything, what the story is. But, you know, we had this whole period of collaboration I'll go into, and he had a tremendous influence on the field that I had spent quite a bit of time on. But I want to say, just in general, as a biology guy, as somebody who wasn't smart enough to be a chemist or a physicist, how much I admire chemistry and how I did some chemistry as an undergraduate and also in my basement in Pittsburgh earlier phase. How the honesty, the brutal honesty of chemists and the usefulness of chemists, and that's the honesty. You know, having, you know, there's a huge gulf. You go across Campus Drive here, there's an enormous cultural gulf, you may have noticed. You know, in medical universe, it's important to be nice to people. And part of the cure of a patient is to not always be completely frank about how bad it is. And so there's a lot of beating around the bush, both with the sort of the patient care thing, which luckily I've never been in, and your colleagues. You know, you never really sometimes know what they're up to or thinking. Whereas in the chemistry world, and I saw it with Harden, particularly one time I had a new postdoc and we were coming out of the immunologist seminar, and I was saying, oh, Harden, here's my new postdoc, so-and-so. And Harden looked down at a somewhat diminutive postdoc, and she piped up and even said, sort of jumping up and down, said, "Oh, Dr. McConnell, remember we met at this island meeting sometime 2 years ago?" And Harden just looked down, said, "No, I don't know." And I thought, that's great. I've just been in a medical school too long. I'm just too used to this kind of circling around with what you're really up to, what you really mean, and so forth. And then the other thing, just in terms of the universes of the cultures of science, as it also relates to that, is it was when I was an undergraduate, I always passed by this building, which was the biophysics building at Johns Hopkins in Homewood campus. And it was a really impressive building, and it was, of course, filled with physicists who had come to save biology. And they were all like building a machine to measure something really, really precisely. And yet, it was usually something that no biologist was actually interested in, or had nothing, really was not germane to solving any particular biological problem. And later on, I realized it's because they never talked to biologists. And then this has been continuing over the years, and we were doing a lot of imaging for quite a while, and people suddenly realized it was it could be considered biophysics, single molecules and things like that. And they invited me to the biophysics meeting, and I saw basically a lot of the same mythologies, and particularly at the time there was a lot of atomic force microscopy, and people were poking some cell or the other, and talk after talk they'd say, well, we poked this cell, and we got this result of atomic force microscopy, and then someone would ask a biological question, which was like, what kind of cell is that? And they would all say, oh, I'm a physicist. I don't. These are details. We have collaborators who handle what question we're asking, things like that. And then to cap it off, it was really fantastic and really brought it all together. Was someone a little more mature at the meeting came up to me and introduced himself and said, well, I'm so-and-so, and I'm a physicist, but I have a chemist's need to be useful. And I just thought, yeah, that's why I identify with chemistry. That's why, usefulness is important, and trying to figure out what the actual question is and how to interface the disciplines, and not just everybody go off in their own bubble and do whatever. So that was something obviously Harden did, and had, as I mentioned, Lisa, our experience, and from what I know, I'm sure lots of other aspects of just how useful it was to apply his intellect, even for fractions of a second, to the things that are tremendously important in terms of understanding the complexity of all these chemical processes. And in looking at the papers and from my own experience, he really became, in the 1980s, interested in this whole problem of T-cell recognition, and something that I worked on almost my whole career, and lots of people work on in the immunology sphere, but it hasn't had the benefit of enough chemistry. And so the problem is basically that a major part of your immune system involves T cells, which are the second form of lymphocyte. B cells make antibodies, and you know all about antibodies, I'm sure. But T cells are more subtle. They are recognizing not just surfaces of proteins the way antibodies are, but they're actually recognizing fragments of proteins, antigens, mainly peptides that could be non-amino acids in general, that are bound to these molecules called histocompatibility molecules, which you'll notice look somewhat like a moose, where these are the so that's the peptide, and you can think of this whole business of presenting peptides of somehow these histocompatibility molecules circulate through the cell, and they pick up bits of protein. And the beauty of that is that those bits of proteins do not have a structure, or they do not have a structure that can withstand the sort of vice-like grip of a histocompatibility molecule. So it basically grabs proteins, whether they're from the cell or they're from a virus, and then what's called presents them on the surface of some cell that's, say, infected by a virus. And that's where T cells come along, and they have these T cell receptors here and here, which are like antibodies, only they're strictly surface proteins. They have the same diversification mechanism. They can make billions of possible sequences, and you basically pre-position all these billions of possible sequences around it, and somehow you're able to encapsulate all the possible versions of peptides that can be bound to these histocompatibility molecules and seen. So the beauty of it is that whereas antibodies can be fooled, that there are bugs that hide their antibody binding sites, hide their most vulnerable sites where antibodies can't get them, every protein has to get degraded, and therefore by capturing just enough information to be fairly unique, like a 9 amino acid peptide, generally the T cell can successfully tell what things belong there, what things don't belong there. If it sees something that doesn't belong there, it can do a number of different things. It can kill the cell if it thinks it's a viral infected cell, or transform cell. Some really exciting work is going on now, where basically people have found ways to induce T cells or allow T cells to kill cancerous cells, and it's a very big field right now. That's just exploding. So that's sort of the general thing of why T cells are important, and I think why Harden got interested in this back in the day. And there are two ways in which we interacted with Harden. One was directly, mainly around questions of how do histocompatibility molecules bind peptides, what do peptides look like when they get there. And that was a direct collaboration, involved 8 or 9 papers, which were great. But there's an indirect way in which he dramatically affected the field, and that was even earlier with the development of these supported lipid biolayers, that basically by substituting this, what we call an antigen-presenting cell, with the planar biolayer, where you could reconstitute specific proteins that you thought were important, and then look at the effect, basically make a surrogate, that you could define biochemically. That's been huge, and because it also enabled things like single molecule imaging and a whole lot of other things that just still is a field, become a subfield in itself, and just all kinds of things that have flowed from that over the years. So it's taken a lot of years to develop that. So just to go over some of the things that happen, and I would say that some of this, someone once told me that undergraduates are the ATPs of the life of the university, and I would extend that to say that graduate students can be the ATPs of research life in terms of bouncing around somewhat randomly, making collisions here and there with various people and things. I particularly think Josh Rabinowitz was kind of the leading catalyst as an MSCP student at the time at Stanford, that he realized just by bouncing around that we had been developing a lot of biochemistry of histocompatibility molecules on the way to trying to make, to develop structures, which took a lot longer than anyone could have imagined. That this fits very well into some interests of his and Harden's and others, Craig Beeson's here, in trying to understand the relationship between these peptides and the histocompatibility molecules, which have turned out to be much more subtle than anyone expected. So the early data using this microphysiometer that was developed here and then later commercialized by Molecular Devices. Craig and Josh, and with our help, looked at the very earliest activation. You put T cells on an activated surface, and that was partly our contribution. Was we had developed these systems where we could make specific T cells very easily in mice, and then you just take them out of mice and throw them directly onto a bilayer or a surface or whatever you wanted to do, manipulate them, and there were lots of science had been built up around that. And the other thing that was that came out of this, and it's really partly, I think Josh and Craig and Harden more than me, realized that because there was a chain of activation from T cell receptor engagement and a series of phosphorylation steps, that the kinetics of that, and particularly the stability at each step of that intermediate, was going to be critical to whether you made it through the whole sequence, because it wasn't just engage the T cell receptor, you turn on a T cell. No, you engage the T cell receptor, then you activate a whole series of molecules have to be phosphorylated in a cascade, and finally they get to some transcription factors that go into the nucleus of the T cell and change the whole program and change the T cell into something else. And it all takes a few minutes. It's not very long, but there are these multiple steps, and they did a brilliant analysis of what would be critical, and particularly the importance of the stability in each of those steps, and how that could build up and end up being a go or no-go in terms of the activation process. And then one of our interests really had to do with what are the ligand requirements for T cell receptors with respect to these peptide MHCs. And there it was very helpful to collaborate, and we could make different multimers from monomers to multimers of peptide MHC in the soluble form, and then look to see which of those activated using the various technologies. And what we were able to show, and what was still true, is that monomeric peptide MHC don't activate T cells, but multimeric ones do. And that was important in terms of trying to sort out what models, how does this actually happen on the cellular level? Again, kind of reducing it to the sort of the key elements in the process. And something that came out of work of Josh's and others in the lab were the realization that actually the active form of MHC, the form that it didn't just sit there, it isn't just a nice rigid structure like I just showed you, that the peptide goes in or goes out, but actually a still unsolved problem is that there's actually some sort of expansion using sophisticated chemical techniques. We were able to show that there's actually some kind of expansion, some kind of it's, as a popular phrase, molten globule form of the MHC that was the intermediate, that bound the peptide. And then it closed down, and then it looks like this nice thing that you see in terms of the structure. We have yet still to have a structure of that molten globule form. Maybe we never will, but this was the first indication of that, and hopefully someday we'll get somewhere with that. And then there was a whole series of other papers later on. It's Schmidt, particularly Peter Pitzon, who's here, showing, in the first case, just showing that there's peptides in the MHC. If you do some sophisticated analysis of those, and NMR particularly, you can see conformational isomers, that it isn't just, again, a fixed thing, but actually is a dynamic complex. And this, other people, Engel Nanoway and others, have gone on to find similar things in T cell recognition and actually define particular T cells that see one form or the other of the same peptide in the MHC, but they're in different conformations. And we're still trying to understand all of what that means, and there's been particularly some interesting work in another group at Notre Dame has indicated that not only is there variation in the conformation of the peptide, but there's reciprocal variation in the T cell receptor binding that peptide, again, an NMR experiment. And that's really interesting in terms of specificity, because we're still trying to figure out how something like the T cell receptor, which typically binds its peptide MHCs, I should have said, in a micromolar affinity, 10 to 100 typically, could be so specific. It's just as specific as an antibody, but you're talking about 1,000-fold or 10,000-fold lower range of affinities. And I remember when we were first trying to define this, I went around to some famous biochemists and asked them, how can I measure this? And they asked me, how low do you think this is? And I said, probably micromolar, must be micromolar, because we can't see it by various conventional means. And they said, oh, then it's not specific. Don't forget it, it's not specific. But it is specific, somehow. It's sensitive to methyl group changes. Oftentimes only a single antibody, a single amino acid in the middle of the peptide is critical, and if you don't have that amino acid, you're done. Nothing's going to happen. So there's still some interesting issues in T cell specificity that were started with this work and have still a ways to go. But then the other thing, the indirect thing that was incredibly important. I mean, I think these things are all important in terms of defining MHC binding to peptide, really analyzing, thinking about the chain of signaling that has to happen with T cell recognition and other aspects. But the thing that really has ignited a whole area of immunology and particularly molecular immunology of T cell recognition and greatly benefited us, what weren't direct collaborations with Harden, but made use of this sort of amazing thing in science where you build on everyone builds on everyone's work, and it's kind of like people lay the foundation. If it's a good foundation, then someone else will put another layer on that, and someone else will put another layer on that, and how we have this, these wonderful understanding of so many complicated things today because of this sort of succession. And so this was pivotal in the early 1980s that people in Harden's lab, Brian and later Tanya Watts, developed this planar bilayer, the supported lipid bilayer, as a substitute for the antigen presenting cell, and as a way to both understand the chemistry of T cell recognition and peptide MHC and laying the groundwork for these things. That this is should be right. So this is a bilayer. This is something like the bilayer, and you're basically putting these lipids on a glass surface, and this is one iteration, one of the more recent iterations, but it's basically the idea is you're putting lipids on a surface, and then you're putting, this is a somewhat lurid version of a peptide down to a compatibility molecule, or MHC here, code name UK. But, and then later on, you could add anything you want in the way of soluble proteins. GPI-linked proteins were popular at one time. But the basic thing is that you have a defined interface for which you can study the effects of different components or different aspects that you can manipulate in this bilayer interacting with the T cell. And T cell comes down, and then if it likes what it sees here, it activates. If it doesn't, it doesn't, or all sorts of variations. So it really has enabled, on one hand, a way of reducing the complexity of this cell-cell interaction. And I would remind you that in biology, in case anyone's looking for things to do, the biochemistry of cell-cell interactions has been, in some ways, the last frontier of fundamental biology, because it's been so difficult to work with it that, you remember that the first step of most biochemical protocols is to lyse the cells and then purify the protein and then put things back together. And that works great for soluble molecules, but it doesn't work great for cellular actions where as soon as you dissolve the membrane, you've got nothing. That all this cooperativity, all these molecules that work together for one cell to recognize another, you've destroyed that substrate. So that's what's made this a difficult problem and kind of an attractive problem for solving. And what has come out of this, it took about 15 years of development, and long after Tanya and so forth had finished with this and shown you could get basic T cell activation, it took another 15 years for particularly Mike Dustin, then at Washington University, to take this up and say, let's do some imaging here. Let's use some of the recent sensitive microscopy techniques, and then we were working on the other end with similar ideas. Although we started with cells, and then we started to work with Mike, and realized that putting mobile membrane-bound proteins like GPI-linked, MHC, and other things really made it a dynamic and powerful system. And then things like turf microscopy came along, where this was just perfect because you've got this very short distance that you can get single molecule resolution basically if you need it in this kind of situation. And so it's led to just an explosion of information, and as I say, it's something my lab took particular advantage of, but many other labs. There are probably thousands of papers now using supported lipid biolayers to understand both T cell recognition and requirements for activation, also NK cells, some other cells, and just some of the stuff that has come from this has been we were able to show that a T cell can recognize a single molecule of peptide MHC by labeling the peptides directly. This happens to be on another cell, but also on a bilayer. And particularly on a bilayer, we were later able to do single molecule prep between a label on the T cell receptor and a label on the MHC. None of this would be possible without this bilayer technique. And we also used super resolution microscopy to define what we call islands of T cell receptors and peptide MHC on these biolayers. So, and on the T cells that we're seeing the biolayers. So it's really, this field is still going on. There's still lots to do in terms of defining the molecules and so forth. But this all came from this early, really brilliant realization that we really need to reduce to understand cell-cell interactions, to be able to reduce the complexity, to be able to manipulate at least one side of the equation is really, really important. Now, unfortunately, this hasn't worked on the T cell side because the T cell side is more complicated. It requires energy, it requires cytoskeleton, and who knows what else. And that still remains to be cracked, but ultimately, I bet someone will do that and will have even better picture of what's going on. So I think that's all I wanted to say. And I think, thank you.
I guess I've often wondered the fact that Harden never ventured into a commercial operation. And I was thinking when Hayes Griffith was talking and saying that Harden was very competitive, you have to remember at the time that MBC started, there were a lot of Stanford professors starting their own little companies. So I think maybe this was just competition. He wanted to also get in and so he could talk about his company. Anyway, always huge fun. And so I'll start with telling you, I was actually in the McConnell lab for 10 years. I started off as a graduate student. I got my PhD fairly shortly afterwards because I was actually transferring from San Jose State. So to start with, I'll just say how heroic it was that Harden actually took me on. I was 33 years old, I had 2 young children, and I was transferring from San Jose State. So I think the clinch was I knew how to immunize rabbits. So it wasn't the first thing I did, but I did get into producing antibodies for tempo, for spin labels. And so we did a lot of things with those. But it's also, if we're talking funny McConnell stories, it's also the situation that he had this ranch with a bunch of goats. And one day he said, well, we're going to immunize the goats, it's important. And we never actually did anything with the immunized goats, but I think it had complicated tax reasons. But there was one day he said to me, okay, and my colleague, Philip Roulet, so he said to me and Philip, we're going to go up and immunize these goats. So I get together the syringe of stuff, spin label and adjuvant, and we first swing by his house, and he picks up this bag, and we get back in the Jeep. This was the old red Jeep that people make with the gunshots through it. So we pick up this bag, we go up to the ranch, and through the gate, and he's wearing a cowboy hat. And Philippe Roulet, who always had his fabulous French accent, said, "This is my first cowboy." Then we get out, we go to the gate, we get out at some little house thing, and he opens the bag, and sure enough, there's a gun in it. And he then explained to us that there'd been people lurking around, and he thought he'd better be armed. So, and Philippe said to me, I knew it was a gun. I thought he was going to shoot me. He had a very funny relationship with Philippe Roulet, who unfortunately is dead now. It's very sad. But anyway, Philippe had this fantastically funny relationship with him. He used to do fencing, so he was fencing for Stanford. And Harden said, why do you waste your time doing this? And he says, once I get my PhD, I'm going to cut off your head. Anyway, so continuing on the goat story, we get to the goats, and they're sort of big, fierce goats. So McConnell wrestles these things to the ground, and he sits on them, and I'm there poised with my syringe, with a spin label. And there's the goat's bottom and McConnell's bottom. It's moving around. Unfortunately, I got the goat. So anyway, having got my PhD, which was 2.5 years later, because I'd already got a master's degree. So I stay on as a postdoc and a research associate. Now actually in the middle of this, I wasn't the full 10 years, because somewhere in the middle, about 76, 75, 76, I spent 6 months in England in Martin Rath's lab, and working with him and his colleagues, I got to know a bit about cellular immunology and techniques to fiddle around with cell culture. So when I came back to Harden's lab, he was good enough to let me set up a cell culture facility in the lab, which irritated a lot of chemistry professors. In fact, one of them, a very eminent Stanford chemistry prof, once stopped me in the hallway and said completely seriously, "You are a very bad influence on Professor McConnell. He should not be doing these sort of things." And I was dumbfounded, you know, I couldn't say anything. It's one of those situations you think, my God, I wish I had been faster on my feet at telling him something. Anyway, that was fun. And so that was when the rot set in and we started doing cellular immunology sort of stuff. Then I was actually 24 years at Molecular Devices, and it was an interim period when I got an NIH grant with nowhere to take it except the Institute for Medical Research in San Jose. I couldn't leave the area. Anyway, it was altogether fun. Let's find the next slide. Okay, so Harden's interest in developing and commercializing assays probably started with Seaver. This was a diagnostic company spun out from Syntex and Varian sometime around 1970. So McConnell, Gerasi, and Avram Goldstein from pharmacology were also involved. The initial products included a spin label-based assay for opiates in Europe. The assay was invented by Avram Goldstein and his colleagues. This was used by the military in Vietnam for testing soldiers. Betty Gaffney says that military personnel learned to use ascorbic acid to fill the assay, which probably they needed to do in the Vietnam War. Anyway, so this is courtesy of my 3-year-old son's colored pencils. The Seaver assay for opiates. Probably many of you are familiar with this. All you do is to take a spin-labeled opiate, mix it with an antibody specific for the opiate. You obviously essentially immobilize the spin label and you flatten the spectrum. Whereas if you have competing opiate in the solution, you'll compete with the antibody or compete with the spin labeled opiate, and you'll get a sharp spectrum reappearing. So very simple assay. Now, when I first joined the lab in '71, Harden told me about this, and he said, "This has got a problem. It doesn't have gain. You've got one antibody molecule, one opiate, and let's figure out something with better gain." So, whoops, wrong thing. So this is an assay based on antibody complement lysis of liposomes loaded with concentrated spin labels. This was the first thing he set me to do. So this is supposed to be a liposome. It was multi-lamellar, actually, it should have been shown here. And it was filled with soluble spin label with tempo, and on the surface was an antigen. And you treat it with an antibody specific for the antigen and complement, and the whole gets put in the liposome, and you release spin label, and you get a sharp spectrum, whereas previously it was flat because it was concentrated, and you removed all the outside tempo. You obviously had to load it and then dialyze the outside off. So in contrast, if you mixed in some analyte that was the same as the analyte down to the liposome, you got inhibition and your liposome stayed complete and you stayed with a flattened kind of spectrum. So that was totally impractical. And so we filed a patent on it and sold it to Seaver. I don't suppose they gave us much money for it, but that's fine. So it must have, lipid membranes in amino acids must have still seemed like a promising idea to Harden, because what he's written in Adventures in Physical Chemistry is, in 1983, I founded Molecular Devices Corporation. My original idea was to use a bilayer lipid membrane on a silicon sensor to detect immunochemical reactions. So the founding of Molecular Devices is in 1983. Sutter Hill, a venture capital firm, gave Harden $500,000 to start NDC, based on the idea of using monoclonal antibodies and silicon sensors for point-of-care diagnostic purposes. This followed an earlier McConnell venture, DNAX, with similar goals. Then DNAX was acquired by Shearing Plow, who were not interested in the project. So Harden hired his former postdocs, Wally Pass and Dean Haveman and me, all on a part-time basis for the first few months. He rented space on Porter Drive, Stanford Industrial Park, from the Linus Pauling Institute. It happened to be good that we had such an eccentric kind of environment. Now, just let me tell you about my colleagues here who were involved in starting Molecular Devices. First is Wally Pass, who is sitting out there somewhere. Wally was 3 years in the McConnell lab, 1976 to 79. He was 12 years at MDC, 83 to 95. And he was always involved in research. His first 4 years were half-time because Wally held faculty positions at Wake Forest University Medical Center from 79 to 92, and he had overlapped, he had a complicated situation, but anyway, he kept going, which was great. And then Dean Haveman, who had a similar situation, he was 3 years in the McConnell lab, 78 to 81 as a postdoc, so he overlapped with Wally very much. And, well, no, he overlapped again. So then he was 17 years at MDC from 83 to 2001. So Dean was always involved in research and also intellectual property management. Dean also held faculty positions at Wake Forest. And so, very early on, Wally, Harden, and Dean invented this at Molecular Devices. So this is the basis for cytosensor that we were talking about earlier. And let me try and explain this thing. Here's a piece of doped silicon chip with a special insulator layer, which is nitride. And on the surface of this are hanging off amino and hydroxyl groups, which get titrated to reflect the pH of whatever you've got in this electrolyte solution. So it's a fluid electrolyte here. And so these charge is, as I say, a function of the pH. Now, underneath the chip, we've got multiple LEDs, and only one of them is shining at the time, and it's being pulsed on and off, so it's fluttering a little bit. Now, under certain circumstances, you can get electrons to flow back and forward in this little bit of circuit and affect the ammeter. So you're trying to pick up when the ammeter is going to tell you you've got a current flowing. So, in order to induce this to happen, you have to get the potential that's being applied to the electrolyte solution to be correct, so you get a depletion layer underneath the insulator. And what you're measuring actually is the potential at which you start this little current running back and forward. Now, this potential, the potential that you apply to make that happen is going to be affected by the surface charge here, so therefore it's affected by the pH. So you can see this just this little section is where you're going to be picking up whether the current is running or not. And that would be a function of the surface charge and the pH exactly at that spot opposite the light that happens to be shining. Now, if you, instead of this light, you light this one, switch this one off, you're looking at this surface potential and pH at that side. Okay, so that was okay. Anyway, you had to develop the chip, and this was fairly complicated, and it still is. And Wally and Dean, I think, are still sometimes sent back to, go back to molecular devices to help with this development. So this happened to be a pretty hazardous bit of chemistry. So at one point, I think Wally, Dean, and Harden were setting this whole thing up. I realized they were all crazy, and so I was in a different room. But I think what happened, I was probably the closest person to this explosion, because I think they'd all taken off down more. There was this very impressive explosion, followed by a roaring sound. And I went to the door of the lab, and there were these flames shooting out of a glass vessel. And they were annealing silicon chips in a glass chamber at a very high temperature. I think you said 400 C? 1100 C. 1100 C. Okay. 1100 C in flowing hydrogen. Okay. And I think as Wally says, Harden was getting impatient that they should start heating. You know, they had to flush things out first, but he was impatient anyway. We couldn't have quite the explosion. I guess it's anywhere but the Linus Pauling Institute, we might have been thrown out. Yeah. So I say, guess it was in the middle of that. So applications of this lab's technology. In general, most of the applications that are still existing anyway are multi-site immunoassays. These are all basically enzyme-linked immunoassays in which the enzyme used is urease. So you give urease and urea, and the pH is going to go up. So the first application I'll talk about is the MPC threshold system for detecting contaminants in injectable biologicals. And that's still being sold and still brings NBC quite a few million a year. Then there was the DARPA grant, which we'll come to in a bit, but that led to military use for biological and chemical warfare agent testing. And we understand that's still being used because NBC still gets orders for reagents. Again, I'll talk about that a bit later. The technology was also licensed to both Abbott and DuPont, but that didn't follow through much. Then there were the real-time light cell-based assays. Again, this was an objective of the DARPA grant, and our research group, Wally and Jack and Dean, worked on that before we started the development of the MDC cytosensor microphysiology system. So I'll just tell you a bit about the threshold system. So this is typical of how the immunoassay works with the labs. Here we've got single-stranded DNA, and I should say this system, this assay, has been accepted by the FDA as a way that people should test for contaminating DNA. That's a big issue in injectable biologicals because the fear is that you could have oncogenic DNA. So you want to show that you've got very, very little DNA. So what you do is take your sample of the injectable, heat it to above the melting point of DNA, and then rapidly cool it, and you've got single-stranded DNA. If you mix that with an antibody to DNA that's coupled to urease, and also with a single-stranded binding protein, which is a magical thing, connected to biotin is coupled to biotin and also streptavidin, then you make a complex and you filter that complex through a membrane onto which biotin is attached. So you then get this complex bound to biotinylated membrane, and you can add urea and form the ammonia, raise the pH, and you detect that with the light addressable potentiometric sensor. So that's what's used in threshold. It's also used in the military use. Okay, so this is what a threshold looks like, and as I say, it still exists. You've got here four places where you can filter your suspensions and catch the analyte on these sticks that have got biotinylated membranes on the end. You then take the stick and you put it in a reading site, and there's 9 samples going to each of these. So you get a recording, and as I say, it just sort of sells itself at this point in time because it's the standard thing that injectables get tested with. So then an important thing to us was the DARPA grant for labs applications. This was a 5-year, $14 million grant covering the 1990 to 95 period. So how this arose was that first Harden promoted the technology to Iris Gernick at DARPA to initiate the process. And the principal investigator was Wally Pass, who followed up on the opportunity opened by Harden and went off and talked to Iris Gernick and got the deal. So it was development of technology permitting early detection of biological and chemical warfare agents. So a third party developed a continuous tape version of the threshold type assay. And the systems were installed on lab on wheels Humphries vehicles. And apparently these are still operational because MDC still supplies reagents. Now we'll turn to the bioassay type application. And this is kind of a complicated diagram. It's from a science paper, a really good science paper by McConnell, the Whitney, Pass, and others. And here I'll point your attention to a receptor being activated by a ligand, which leads to a whole bunch of metabolic processes, in the end squirting out hydrogen ions, picked up as acidity by the lab sensor. And we did, so I haven't talked about Jack yet. So Jack is the 4th member of those of us who were first in the McConnell lab. Jack was there from 76 to 79, the same time as Wally. And then 11 years at MDC, 86 to 97. Jack studied the use of labs for bioassays. He was very much involved with the early work on extending the use of labs for bioassays. And I'm sure a lot of his research was supported by the DARPA grant. I think this is all right, isn't it, Jack? That's really what it came from. And in consequence, Jack supported the cyto sensor once we got that on the market. And then eventually Flipper, which some of you may know about. So Jack gave great academic style seminars about MDC products at conferences and that. I should also say that Jack put together some fantastic Monty Python skits. A memorable one was, "I'm a lumberjack and I don't care." I suppose he's not going to do here. So between the McConnell lab and MDC, Jack held faculty positions, assistant and associate professor in biophysics at UC Berkeley. So that was a very prestigious thing to be doing. So we come to the cyto sensor, and Mark was talking about using it. And it actually had only about an 11-year lifespan because although it did some fairly clever things and it picked up cell responses that you really couldn't pick up easily by any other means, for example, orphan receptors. People had proteins in cell membranes that looked like they were receptors. They had to be Fc receptors, but you didn't know what the ligand was, and so you could use cytosensor to actually discover the ligand. Unfortunately, it really wasn't very commercial. It did all right for some time. I will also say it was the sort of sizzle that allowed us to go public in 95. So it did good things for us, and it was a lot of fun, but its throughput was low, it was difficult to maintain, it was expensive, both to buy and run. So, but I'll just tell you a bit about the insides of it. So, this is the silicon sensor, this is the LED, there's only one LED in a cytosensor situation. The cells are trapped between two membranes in a disposable capsule. This is a plunger that you put down with the controlling electrode in the middle, and the reference electrode is off to the side here. And so this is, again, the cell chamber in the middle here, and just the fluids and start to flow, solution over it, media and reagents. One of the tricks was to use cell media that had only about a tenth the buffering capacity of what you would use for cell culture. And what you're trying to do is to figure out the acidification rate of the cells. And to do that, you had to flow fresh medium through, then stop and measure the rate at which the pH dropped, and then turn the flow on again. So it's flow, stop, flow, stop, flow, stop. And that's the basically the pH versus time. And this is the acidification rate. And you'll see at this point you've added some stimulating agent and it's gone up. So that's the type of data you'll get. So some of you may say, but MDC is a microplate reader company, how did that happen? And indeed, always the main source of revenue for molecular device product, the revenue that is. Obviously, in the early days, we got grant money was predominant. But once we actually had products, the microplate reader was the first product, and those readers always made more money for the company than anything else. So it started in 1984. It was somewhat accidental. I don't know what a business department course would say about it. Anyway, all we really knew about was working in research labs. The company had kind of been set up to do point-of-care diagnostics. And although we hired in some people to try and help us do that, they all sort of faded away, and all our things with Abbott and DuPont went away. So really, those are guys who were the core of the company, because for a long time we didn't really have a proper CEO. We were just a sort of weird bunch of people fiddling around in the lab. The venture capital people would sort of send in people to try and look after us from time to time. But we really didn't have a full-time CEO until Gary Steele, and we got rid of him too. So it was like herding cats, you know, it was like herding cats. So anyway, all we really knew about was working in research labs. We needed pH-based assays for testing the labs. And developing immunoassays would be time-consuming, complicated. We didn't really know what to assay for, whatever. So I knew that traditional bacterial ID assays are based on pH changes in selective growth media. It seemed like me a useful application to pursue. So I acquired the stable of bacteria and set about running the traditional colorimetric assays. To record my results, I wanted a microplate reader, but couldn't afford one. However, while indeed had built a 96 LED assembly to use with a big vat chip, they'd chosen the 96 LED assembly to be just like a microplate because they thought people would be pipetting. It's the standard format for all stuff. So anyway, let's move to the next one. So just as a refresher here, remember you've got you've got a lapse chip, you've got the insulator at the top, you've got the LEDs underneath it. Now, what we'd be measuring with the lapse is the pH here, but I think you can surmise that if you kept the pH constant, then the potential at which you measure this thing would depend on the light intensity. So, what I was able to do was to turn this thing upside down. So this is our first plate reader. This was the 8 by 12 green LED array. This is the lapse chip, but it's turned upside down, so the insulator layer is underneath, and there's a buffered agar slab under that. And then all the electronics is connected exactly the same, but everything's upside down. And from that, because they've also got the software that would record results, we could see, I mean, it wasn't a full 96 well plate because the chip wasn't big enough, but anyway, we could see a kinetic display from many wells, and we thought this is really cool. But it was a distraction from what we were supposed to be doing. So one day, Harden said, Gill, I'd like you to look after this microplate reader thing. And he really wanted Wally and Dean to concentrate. I didn't know anything about his electronic stuff and all this stuff. So anyway, it kept me happy. And we knew Wally and Dean still kept very much involved with it. We needed a very rapid reading rate, all wells measured at almost the same time, temperature uniformity across the plates, software compatible with monitoring all wells, displaying kinetics in all wells. We assumed at the time that the ELISA, enzyme-linked immunoassay, which was the most important microplate application at the time, would be improved by kinetic analysis. As you'll see later, that was not right. And so, the initial idea was to have a very low-cost price reader using LEDs and silicon photodetectors. It turned out for very technical and market reasons, it wasn't a good idea, and we wound up making the most expensive one instead. So it was a difficult birth. By then, at some point in, after some months or a year or something, Gary Steele, our first full-time CEO, say later we did fine, said, Jill, I didn't need Genentech to be CEO of a microplate reader company. And then he tried to, at this point in time, Hewlett-Packard and Genentech, Hewlett-Packard sort of went to Genentech, I think, and said we should work together to develop instruments for biotechnology. This is a good market, we need to do these things. So Gary Steele tried to offload the whole microplate reader project to Bob Ward, who was the CEO of APG, and who said, the world doesn't need another microplate reader. You probably all read all this down here. And when we did a market survey, it's true that the contemporary reader users said they couldn't think of any reason why I would need a kinetic microplate reader. Fortunately, I didn't actually tell people much about this. I had a colleague by then who was at young Harvard MBA, so he fortunately was sort of believed by the CEO, and fortunately he also kept this under his hand, so that was fine. So, then how did this survive at all? So I think it had a microplate reader guardian angel, I think. At this point, Harden still had a controlling interest in the company, and he kind of thought this was cool. And so he must have been the support that allowed us to keep going with this. So we persevered most of the time. Oh, am I running over time? So I'll try and go fast here. We sold a lot of these VMATs. They first came out in '86. We sold a ton of them. Kinetics wasn't a great selling point at all at the beginning because you get in an ELISA, as the color isn't produced in a homogeneous way, and even if you shake it, it doesn't work very well. So I'll get through that one. That was Calvin Chow, who was so very important, me and Dean. And so why was BMAT successful in kinetics wasn't that valuable? It reads very fast. It coincided with the general availability of PCs, including the first portable one from Compact. This allowed it to be demonstrated very easily. And it's still on the market after more than 28 years, which is pretty amazing. Kinetics really took off when we extended the wavelength to 340 and could start doing things that otherwise would only have been done on a spectrophotometer. We became the kinetic microplate company. And we actually took over a lot of the spectrophotometer market by expanding the capabilities. Unfortunately, it was not easy to patent many features, and so we relied on being first to market with new capabilities and applications. Because that can only go on so long. There is one exception, which I'll mention, because again, this is Dean, who was part of the McConnell lab, and he invented and patented path length correction on the microplate readers, and this means reading at long wavelengths and subtracting the OD at 900 from the OD at 977, and using that figure to correct the path length. And then you could get some quantitation, primary quantitation of the plate reader. So our kinetics reputation helped us acquire Flipper. Does anyone know what Flipper is? No, we don't. Okay, so fluorescence imaging plate reader. It was very important to pharmaceutical companies because they could do high throughput calcium flux assays. So this sort of killed cytosensor actually, because now you had a way that you had high throughput way of doing cell-based assays and looking at the responses of live cells to various agonists and antagonists. Almost through. So NDC went public in late 1995. Harden stayed on the board, and we acquired a company that makes Flipper. Flipper is a plate reader, but it was selling for $500,000. I mean, this is a big plate reader. And acquisitions became a focus of the MPC strategy. In conclusion, when it was sold to NDS Analytical for $600 million in 2007, NDC had more than 1,000 employees and $200 million annual revenue. This ended Harden's relationship with the company he founded in 1983. He remained interested and involved until the sale was completed. He did come round very often and sit and chat with me and ask what was going on. Although, clearly, even after the IPO, I think his interest sort of waned a bit. So, that is the end. Thank you.
When I tell people that I was a postdoc here from 97 to 2000, a common response is, did you like Stanford? And I tell them that I had a somewhat love-hate relationship with Stanford. I loved working in McConnell's lab. One of the ways that I came to work in McConnell's lab is that I applied for an NIH postdoctoral fellowship and was granted it. And then I soon learned that I would be needing to pay tuition at Stanford.
Oh, God.
And I called up the NIH and I said, Stanford says it needs some tuition. And they said, you're a postdoc. They don't have tuition for postdocs. I said, no, they do at Stanford. And they said, that's impossible. And so I inquired, and they said, no, this is a special postdoc tuition. This is such a special postdoc tuition that you can't actually use it to go to any classes. It's a special kind of tuition, for which the NIH said that is not allowed. So Harden went to bat for me and somehow found me the money, and I don't know the exact story behind that, to pay my tuition that was not allowed. And I hear that Stanford no longer charges its postdocs tuition. And that's marvelous to hear. Okay. Earlier this year, I was giving a talk at the University of California at San Diego. And there was a guy in the audience who I won't mention, and his initials happen to be Stanley Appella. And he said, so of all the things that you're talking about, what of this did Harden not consider in the 1970s? And I think that is a very unfair thing to ask. It's extremely difficult to find a research topic that Harden McConnell had not possibly considered in the 1970s. So let's go back to the 1970s. I was going to start out with Roger Kornberg's suggestion for how these talks might be structured. What were his contributions, what was the impact, and what is the current state of the art? And I'm going to apologize right now because there are so many people in this room who have contributed to this field, even this part of the field, and I'm not going to talk about everybody's and all the collaborators. So I apologize right there. One, lipid flip-flop. So Roger told you about flip-flop, 1970s, and the surprising result that the half-times of flip-flop, very long, 8 hours over the half-life of that, and that was for spin-labeled phospholipids without cholesterol. And I would like to tell you how that's still very interesting today. And that's particularly interesting in membranes containing cholesterol. The cholesterol flip-flop rate is orders of magnitude shorter. So this is by Ted Steck, Lon Lang's group, so on the order of milliseconds. It's amazing. And there's still a very open question in the field about what the flip-flop rates of lipids in the presence of cholesterol are. So this is an active area of research today. Just about a Biophysical Society meeting this year, I heard about simulations by Peter Thielman. I heard about plans for neutron experiments, but the case is not yet closed on this chapter that was opened in 1971. Something that we've not heard so much about today are coexisting phases in model lipid membranes. And so by model lipid membranes, there are many possibilities that we can talk about. There are monolayers and bilayers. And so as we heard about before, here's a case where there's a monolayer containing a gel, a solid phase. And you can tell that this is not a liquid phase because we don't have circular regions. So we have an ordered phase with a disordered background. And some of the early work in this field, 1975 here, is thinking about a bilayer system. And this bilayer system, oh, look at that, I made the two same things, I apologize. This is DEPC for the unsaturated one, and DPPC for the saturated one, and there's gel-liquid coexistence. So as you go to 100% saturated lipid, that one has a higher melting temperature, and in the middle here is a gel-liquid, solid-liquid coexistence region. Now, when we think about the work today, we're thinking about membranes that contain high amounts of cholesterol. So now we need to think about a ternary phase diagram. This diagram is showing all temperatures. This one is at only one particular temperature, and all possible compositions of those three different components are found within a space within that triangle. So the work before was showing you at, say, 23 degrees, a cut through here. Over here there should be gel, then there should be gel-liquid coexistence, and then there should be a liquid phase over here. What happens now as you travel up in cholesterol space? And what's the motivation behind this? So we had a conversation at lunch about the question of, do you believe in rafts? I think that the conclusion that we came to was that you don't have to, but it still makes a lovely motivation. So here's the historical view of that. Is Mark here still? No? Okay, he's escaped. So the idea is that the plasma membrane of a cell is supposedly not uniform. Perhaps, maybe, it contains raftones. I don't know what they look like, so I've drawn them as little red squiggles. And if they do exist, it leads to a nice question about what are the what could distinguish the lipid composition inside the raft domains from those outside of the raft domains. Okay, now let's think about those parts on the phase diagram, and I'm going to think about this one actually in terms of, to try and go in a more chronological order, to think of Harden's contribution in monolayers. Here we see increasing mole fraction of cholesterol, and now this is surface pressure. Okay, so we normally think of pressure in a unit of force per area. This is one dimension smaller. So this comes in something like newtons per meter to perhaps most of you, except if you're working for McConnell, in which case you bring him your data, and he says, bring that back to me in God's units. Because God likes to think in centimeters, and God likes to have masses in grams. So you bring back your data in the correct units to show you what's happening. So the idea here is there are two coexisting phases down here. There's one liquid phase up here. So a picture taken down here will look like that. And Arun is going to tell you right after this maybe what happens as you keep continuing on in that particular phase diagram. That's for the saturated lipid, picture of the saturated lipid and cholesterol. And what about for a place where there's an unsaturated lipid and cholesterol? A note here is that if you're on this binary axis, by definition, the difference between those two phases is that there is a cholesterol-rich phase and a cholesterol-poor phase. I'll come in just a minute. Here's John Hagen. John Hagen is here. Where did you go? There you are. And here is your phase diagram. This is with an unsaturated lipid, so that's an unsaturated version of the MPC. And again, there's a two-phase region down there and a one-phase region up on top. Now, that idea of cholesterol and cholesterol poor had a huge impact on the field because it really led a lot of people's thoughts about what might be happening in cell membranes, that if there are such things as rafts, that they should be cholesterol rich and cholesterol poor. And that also led to an assumption that depletion of cholesterol from cell membranes, by whatever means, perhaps with cyclodextrin, simply deletes those raft domains. And that's an assumption that can be tested in model systems. So let me tell you about one particular model system, and then I'll return back to this idea of testing that. Something that's happened recently that has also changed the field and changed our ability to manipulate different membrane systems is a discovery of micron scale, so marvelous for microscopy, domains, coexisting liquid domains in vesicles. So here we have a vesicle in which we can see two different domains. This part is a liquid disordered phase, and it is immiscible with a liquid ordered phase. And that was discovered in the labs of Nancy Thompson-Tent, James and Enrique Graton, followed by some work in Fred Cohen's lab, and we were soon after, so that was really gratifying. And when we entered this field, we assumed that the difference between these two phases is that one would be cholesterol rich and the other one would be cholesterol poor. And that's how I definitely thought of these two. And how would you answer if that's really the way that they're different? Is to use a phase diagram. So use those same tools that McConnell taught us. And now to take all of that data and notice that this region in the middle, again, we're at only one temperature. These different regions represent different ratios of all those three different lipid types. And the liquid-liquid region is in here. And the thing to notice is that if you draw a tie line, what is a tie line? It tells you the endpoints of those tie lines tell you what the composition of the two phases are. And that tie line is more horizontal than vertical. And that says that the primary difference between those two different regions lies in their phospholipid content, not in their cholesterol content. And that was a big surprise. Okay. I'm going to tell you about 4 different topics, and they covered the first 2 very quickly. The next one I'd like to talk about is lateral diffusion in lipid membranes. So we already heard about the contributions of Philippe Deveau, and in particular of finding that the lateral diffusion coefficient for a single lipid within a membrane is on the order of 10⁻⁸ centimeters squared per per second. Now, that was followed by work showing that, well, it depends what the state of the membrane is in which that lipid is diffusing. What if the state of that membrane is a gel phase? Then you would expect the diffusion constant to be much lower. And there's some beautiful data here showing that a system that at 21 degrees, so this is diffusion constant going up on the y-axis, this is mole fraction of cholesterol. So let's start on the left-hand side here where there's no cholesterol in the system. We're going to look at a system that is in a gel phase at a particular temperature. This is a different system that's at a gel phase at that particular temperature. And now start adding cholesterol. An effect of adding cholesterol is to get rid of the gel phase in the system. So we start adding, and whoosh, starts moving much faster because now we're in a liquid phase. Same thing here, it doesn't matter the particular liquid type, the phenomenology is the same. Now, let's take that work in a model system and apply it to thinking about diffusion of lipids in a cell membrane. And this is work by Maria, working with Stephanie and Debbie, and they did some gorgeous work. I love this paper, Maria. And it's showing a cell system. And of course, if Mark were here, he would ask you which cell it was. And up here, at a large amount of cholesterol, which she could, what's beautiful about this paper, okay, one of many things that's beautiful about this paper is that she can add and subtract the cholesterol to get reversibly the amount of cholesterol in the system. Oh, there you are. And saw that as she depleted the cells of cholesterol, then the diffusion coefficient went way down. And this is wonderful. Again, it's this idea of what can you give the community that they can use. So in use at the time was an assay for rafts or for whether a protein was raft associated. And the idea was you would look at the activity of a particular protein, you would deplete the cell of cholesterol, and then you would see if that activity went away. And what Maria showed so lovely is that if you have a cell system and you severely deplete that cell of cholesterol, you've just made a gel phase. And it's very likely that that membrane protein is going to act in a different way that would have nothing whatsoever to do with whether or not the membrane contained rafts or not. So giving a nice quantitative questioning of that assay, I think, is a big contribution to the field. Okay, let's switch gears and now think about diffusion in a monolayer case. And not only switching from bilayers to monolayers, but switching from individual lipids to entire domains that are diffusing. This was work in 1987, and looking at the diffusion of that domain in the monolayer. So we're looking down on the monolayer. What you'd really like to track, instead of a field of domains, you'd like to track an individual domain. So you need to clear out all the other domains and end up with only one domain. And this is a technique, was it invented by Jürgen?
Yeah, we did it together.
We did it together. So Kai and Jürgen invented this beautiful technique of having an electrode over the monolayer. And because the monolayer lipids have a dipole moment that's associated with them, that can gather or push away individual domains. And that beautiful tool enabled some lovely experiments, one of which is watching the Brownian motion. Now again, we're looking from above. This is the XY plane. The Brownian motions of individual domains through that monolayer. And the conclusion is that they move in a stochastic Brownian way that you would expect. Now, let's switch gears and think about how this is relevant. What's the impact on current work? So when we think about diffusion of domains in a bilayer, now it's slightly different. There's a bit more viscosity due to the solvent on the other side, and there's the entire bilayer, which is going to have a higher membrane viscosity. There are two regimes in which you can think about this theory. One is if there are small domains traveling through a membrane of very high viscosity, so you're pushing your way through the crowd. Another one is to have very big domains that are training a lot of water along with it. So it's behaving like a three-dimensional beast. And the three-dimensional diffusion coefficient is going to look like a diffusion coefficient goes as 1 over r. And the contributions to this field, getting the actual numbers right rather than just the relationship of the variables, has to do with how do you figure out what those numbers should be for a liquid domain traveling through a liquid background, okay, rather than just a solid domain going through that liquid background. And the big contribution of that was really to Kornberg, who did his thesis with McConnell in 1996. Okay, so having a relationship like this, in which the diffusion coefficient goes as 1 over the radius. So just to give you an intuition about that, you would normally expect that a bigger domain would travel more slowly. Right? So that relationship predicts how a domain should grow. If it is the case that the way that domains grow is that they diffuse around with Brownian inertia, when they meet another domain, they collide and coalesce. Okay? That says that the radius of the domain should grow as time to the something, where that something is equal to 1/3. So now let's see the impact on the literature for that number. A bunch of people have gone out and measured what that value of alpha should be, and they got very close to 1/3. Right? Okay, now here is a quandary. I'm an experimentalist, and I have this belief in truthiness of experiments. I must admit I have a prejudice for the experiments. But here are some experimental results versus a theory by Harden. And by Harden's student. And moreover, it's a theory that I can understand, so it must be pretty simple. So that gave me some good inspiration that there was some science to be done in this field, so we decided to measure it. And conceptually, this experiment is very easy, and I'll spare you all of the gory details about why it's actually experimentally really difficult. Conceptually, super easy. You merely get a gigantic vesicle, and then you quench temperature, and once the temperature is constant, you take pictures at different time points, and then you look at the size of the domains, and the size grow because in between here they've been colliding with their neighbors. Okay, you measure how radius grows versus time. And what that looks like when you do a normalized time log scale versus radius log scale, since the log plot, the slope of that line should give you the exponent, and it's pretty close to 1/3. And we're all very surprised to hear that McConnell and his student were correct. Okay. So this is recent work from my lab. Okay. On the subject of diffusion, diffusion can also be used as a tool to probe trans-bilayer interactions. And there's a lovely paper here. Are either Arun or Michael here? I didn't see them, but okay. I just wanted to tell them that I admire this paper. As the acyl chain, here's the experimental setup. You have a well, and then attached to the base of that well are some acyl chains flopping up, right? They're attached to the bottom, and the alkyl chains are floating up. And then on top of that is a monolayer of lipids. And then there are some molecules in here which are conveniently fluorescently labeled, so you can watch how they're moving around. Okay. Now, what happens as you change the identity of the alkyl chains on the bottom here? Well, it turns out that if you increase the chain length of the alkyl chains, a lot of chains in that sentence, then the diffusion coefficient in the upper leaflet decreases. So there's a coupling between those two leaflets. They're interacting through the hydrocarbon chains. Okay, so where are we today? What is the impact of Harden's work today on this field? Well, the previous example that I was showing you was thinking about diffusion of an individual probed molecule, or a few probed molecules, depending on the labeling system. system. Now I'd like to think about the coupling between the two layers of huge domains, micron scale domains. So I showed you this cartoon before, and in this cartoon, I'm not sure, perhaps one thing that you might have noticed is that we've drawn it so that the domains, the places where there's that phase separation, has the same phase separation in both leaflets of that domain. So both of those are coupled together. Why? And what's the magnitude of that coupling? And how does that arise, given that you could think of a bunch of these chains as olive oil together? What's the mechanism of that interaction? The experiment that we did was to put membranes down on a solid support. So here's a solid support, and then here's a membrane, and then apply, this is in a microfluidic channel in my laboratory, to apply bulk flow and to push it so hard to see how hard we have to hit it until those domains come out of registration. Now, there's a theory for that we developed with Mika Hadija and Tal Han at Princeton University. And using that theory, we can fit how hard do we have to push it? In other words, the threshold shear versus an inverse length, and fitting that slope gives us the first ever measurement of the trans-bilayer coupling parameter that keeps those two domains together. And that's important to measure because there have been theories and simulations in this field, but the numbers that have been predicted have varied over 2 orders of magnitude. Okay, so to give you a sense of just the newness of this, we submitted this paper this week. It went to PNAS, so those of you who are members of the Academy, keep an eye out. Okay. Fourth topic. Critical phenomena. Now, when I talk to biochemists often about critical phenomena, there's a colloquial word for critical, which means like really important, which is true. So I would say then in that case it would be like critical phenomena. Or a critical point is often a place where you get a curve that you're looking at some response versus, say, concentration, and the critical point is in the middle of that curve. So those are not what I'm talking about. What am I talking about? Okay, John, here's your phase diagram again. This is looking at a monolayer. Could be any system, by the way. This is a monolayer in which there are different monolayers of differing amounts of cholesterol. This is dihydrocholesterol. It doesn't make any difference. And then on this axis is the surface pressure. And just to remind you, up here there's one uniform phase. Down here there are 2 coexisting phases. And the star is the critical point, sort of metaphorically and literally in this picture. What happens as you get close to the critical point? Kind of did this gorgeous experiments in which you looked at monolayers and then goosed them closer to the critical point. When you do that, the line tension decreases. You may have an intuition for surface tension. Line tension is 1 dimension lower. So it's like this domain has a rubber band around it, and that rubber band just got looser. And then there's also a difference in dipole density, and that difference in dipole density is also decreasing, getting close to the critical point. So these domains originally start out kind of taut, high line tension, circular. You goose them closer to the critical point, and they get wigglier. But the question is, how? By which path do they get wigglier? Do they make what she called dog bones? Or do you get 3, or 4, or 6? And I read this paper and I thought, this is just such a lovely paper. And so you know that this has to be something like paper envy for Kylie's work. Now these are monolayers, and they're made of a single phospholipid and cholesterol. So is this relevant, right? There's Steve's question. Monolayers fascinating, right? So monolayers fascinating. What are they really relevant to? And so when I joined McConnell's lab, we started thinking about, wouldn't it be fantastic to find relevance to a system that we could really think about. So this is work that I did as a postdoc here with Wayne Pitcher, Ray Hustis. And what I would like to show you is that, yeah, this is what I described to you before. There's one uniform phase at a high pressure, coexisting phases at a low pressure, and then wiggly boundaries near a critical point. So what is this system? These are lipids extracted from the entire bilayer of erythrocytes of 2 healthy human volunteers. We've heard a lot about the work that people did in McConnell's lab, and I would like to say that I, like many of you, bled for my research. I was one of 2, I think, healthy human volunteers. Okay. So I've given you the idea that there is a line tension involved. That's kind of the way you think about a rubber band around that domain. There's a difference in dipole density that says what's the difference in composition between the 2 phases. And these parameters have a constant, and then there's a critical, literally, a critical point, a critical surface pressure versus the pressure you have to be at, and then there's an exponent here. And both of them behave in that same sort of way. It's just that the value of that exponent and the value of the prefactor are going to be different. And there's some gorgeous, again, really paper envy, complete paper envy is this work by Dominic Benjamin, who I've never met. I just need to write him some fan mail, really, and say, this is my 20-year-old fan mail that I've been meaning to tell you for 20 years, that I love this paper that you wrote. And what is it showing? That the line tension, the strength of the rubber band, as you get close to the critical pressure, crashes to 0. Beautifully. With an exponent of 1 in that case. So I was inspired by this, by these gorgeous papers, like standing on the shoulders of giants, of Teddy and Jürgen and Dominic and everybody before. And I wanted to think about how to apply this to an observable in the laboratory. Here are, again, monolayers. And what I'm looking at are the width of the stripes close to the critical pressure. And there are wider stripes at a lower pressure and thinner stripes at a higher pressure. And building on the beautiful theories of McConnell, his students, his postdocs, I had a way to relate the width of those stripes with the parameters that had been measured by Dominic and others, and that parameter as well with that single parameter from my measurements, and got a lovely fit. Okay. So, you always knew, there's been some cases before, you always knew where you stood with McConnell, right? He wasn't one to sugarcoat things. So when I brought a piece of work to him that I was feeling very proud about, right? You never brought something you weren't proud about, right? So I bring him something, I have data, let me show you. And he would look at it, and I could tell immediately, not necessarily by his face, but by what he said. If he didn't like it, he would say, this is a nice bit of physics. And don't tell Mark that my PhD is in physics. Although I'm hired in the chemistry department now at the University of Washington, so I hope I've redeemed myself.
You saw the light, yeah.
Yes. And when I would bring him something that he liked, like these data, I would bring him it, and he would look at it and he would say, this is a nice bit of physical chemistry. And then I'd be like, I have done it. Not only that, but I put it in God's units. Double on that. Okay, critical phenomena. What about bilayers? Where is this field now? So here's results from my laboratory and also Sarah Veach's laboratory. Sarah Veach looks at plasma membrane vesicles. These are vesicles that have been bled off of the surface of a cell membrane. And the point here is that all these phenomena don't just apply to monolayers. This is a bilayer system, those giant vesicles that I showed you before. And what I'm looking at is the correlation length. That says, how big are the fluctuations in this system? And you'll notice that they have a huge rise right at the critical temperature. So this is T minus Tc over Tc. So when T equals Tc, this is 0, whonk, goes through the roof. Okay? And a beautiful thing to notice about this system is that the same thing happens in my model system in my laboratory, containing only 3 lipid types: high melting temperature lipid, low melting temperature lipid, and cholesterol, as it happens in these systems from giant plasma membrane vesicles. So the 2 data sets, the red and the black, are right on top of each other. And as Roger alluded to before, Harden was very excited about this, and it was very exciting to have him excited. And so he wrote in Understanding Membranes, as Roger read to you before, remarkably, the intensity of the fluctuations in the membrane blebs, the red data above, are found to be the same as those expected for the theoretical 2D Ising model. So all of this fits, and so I wanted to give some context for that comment before. And I realized that this is not something that I remember not actually paying terribly much attention to the 2D Ising model in graduate school, because I thought, oh, ferromagnets, fascinating. Failed to realize how incredibly deeply beautiful they are until a little bit later, when I then learned quite a bit about them. Okay, where is this field now? I think that a lot of exciting work in this field is now in thinking about the dynamics. So the 2D Ising model, the way some of you may have learned about it, if you were actually paying attention as opposed to me, in graduate school on this subject, was thinking about the static systems. You take a picture and then you can find things from it. Now let's think about the dynamics, and that's a much harder system because you need to know the mechanism of the dynamics. Thinking about the dynamics is akin to saying, how do you relate space to time? And so we can look at a system that's quite far away from the critical temperature. There's smaller scale fluctuations that are winking in and out of existence on faster time scales. Here's the scale bar to that, and that's approximately real time. Now, if we get closer to the critical temperature, these fluctuations are huge. Remember how the correlation length blew up near the critical point? This is exactly what that is. These are the correlations becoming large in size. They're also becoming longer lived. So we want to relate space to time. Usually when I think about relating space to time, my go-to way to get an intuition is to think about a diffusion coefficient. So I'm going to write a diffusion coefficient in a way that you might not be used to thinking about that, which is here is a 1 over time. Looks like a 1 over length squared. And that gives you a diffusion coefficient that gives you length squared divided by time. Now, we are in the land of critical phenomena. So there's a rate, 1 over time, and that is related to a 1 over length to the something. And I admit I have very little intuition for what the something should be. Okay? And so our dynamic scaling function, which takes the place of the diffusion coefficient, now has units of length to the something divided by time. Okay. Well, okay, fine. That's all right. I don't have a lot of intuition about many different theories. Go read the literature. Fine. All right. So there are a lot of different models out there. This top model is for magnets, right? The ones that I failed to learn very well in graduate school. And it turns out it doesn't even matter. It's not applicable in the dynamic case because it doesn't have the right way of dissipating the fluctuations. We need to have a conserved order parameter. So that means any of these models are fair game. There's one that seems more likely than the others, and that's this one down here. Very recent work in the field by Mikko Hataja, 2009, and Arun Fujitani, 2008. And to save you a lot of details, there's a coupling between the membrane and the bulk fluid. And we expect the something to be to the third. Now, what's the challenge in this area is that there had been no successful measurement of any of those fundamental parameters in a systematic way. So when I was a physics undergraduate, and I thought, what will be my contribution to the field? And everything seemed to have been done. I thought, will I be finding the 10th decimal place on some universal constant? There are these regions where when there are advisors who are brave enough to push you in different directions and reach out to different colleagues, that having these membrane systems turned out to be a way that we could measure these fundamental constants in physics that I wouldn't have thought. Okay, so what did we find? Turns out this one is indeed correct. My student Aurelia Hunter-Kent-Smith, who's now on the market, by the way, a faculty position, who's now a postdoc at University of Cambridge. And what did she do? She measured a time-dependent structure factor for a bunch of different delay times. All of these data collapse with a single parameter fit onto one curve with the correct choice of the exponent, which is close to that. Okay. So that brings us to, just about time to end. That brings us to thinking about the contributions of Harden. Obviously, we've talked about many ways in which Harden laid a foundation. We've talked about ways in which he's inspired all of us. And what I want to remember you when we showed those plots at the beginning of his citations and his productivity, that productivity was high all the way to the end. And so when you look down on his list at this website of hardenmcconnell.org, and look at his huge productivity, what's here in 2012, 2011, he's still thinking about and writing fantastic theory about exactly these sorts of systems, of dynamics in critical systems, of diffusion in systems that are near a critical point. And for those of us who work in these systems, it's such a pleasure to talk to him continually. I'm going to tear up at the moment. This is where Craig Beeson said he was glad that he's not giving the talk. In the past couple of months, when I've had results from my laboratory, I felt this itchiness in my legs to run up to my office. And what would I do there? Why do I feel that way? Because what I want to do is call Harden. I want to write him an email and tell him about the fantastic results that we've gotten, because that's what I've always done. It's been really hard in the last couple of months learning how to talk about him in the past tense. And so I'm so happy to have colleagues now with which I still feel so excited to share my results. So thank you for being here and for listening to us.
Yeah, so I'm going to, going to talk about the last parts of Harden's career on liquid bilayers. And I joined his lab in 1998, so it's going to be 1998 to what was it? Reference 481, which was in 2013 or so. So for these years. So this is starting from 420 or so. It's in the 420s of his publication. So this last day, you're following along. Yeah, you'll see, like, all of the references I have are just the numbers, because it just gets too much. So I came from, myself and Maria, we were his last grad students. So I came from Berkeley, worked in the lab with Richard Matthews, and as an undergrad. And next door to him was David Chandler, who I would meet at late at night all the time. And so they told me that I should go to grad school at Stanford and I should work for Harden McConnell. So I applied to Stanford in biophysics program. Steve Oxer was the chairman of the program at the time, so I came here. First weekend I went and talked with McConnell and said, hey, can I join your lab? And he said, no, I'm not taking any students. So I said, but I persevered and happen to know something about the Pythagorean theorem, which is for it. Anyway, so it worked. So my work focused on something Sarah's already touched on. I'm just going to continue from that. And so on basically, how is this cholesterol molecule organized in the membranes of animal cells? Right? So Sarah talked about lipid monolayers and bilayers. So that's those are the model systems I'll talk about as well. So almost everything I'll talk about will be experiments dealing with lipid monolayers in Harden McConnell's lab by myself and many other people who were there at the time. And then we use lipid monolayers at the air-water interface as a model for the more complicated lipid bilayers, which form the perimeter of all our cells. And so then I'll talk about extensions of the results that were found by McConnell to lipid bilayers. And then finally, I'll make a few remarks on the chutzpah that McConnell had to make leaps from here of what we knew about organization of cholesterol monolayers and bilayers to try to say some things about how cholesterol may be organized in the membranes of cells. The cellular membrane, this is just a model of what a synaptic vesicle surface would look like. Notice, so the green regions here are the lipids. Notice that a typical membrane has maybe 50% of its surface is covered by protein. So, and the lipids that make up the other 50% of the area typically range from, in a macrophage cell, it's about 120 different lipids that are present at least 0.5 mole%. So we're going from simple binary and ternary mixtures to that. So that's going to be how I organize the talk. So let me start with the way in which we wanted to investigate molecular details about organization of lipids and membranes is by investigating their phase diagrams. So Sarah has already talked about some of that. Here's a picture of a gel phase. We're mostly interested in liquid-liquid phase separations. So Sarah showed a related system. It's John Hagen's work again. Those two references. So this is a binary system. Make on the left side is 100% of the phospholipid, 0 cholesterol. On the right side is all cholesterol and no phospholipid. And as you vary the composition, there is a range of pressures or molecular densities, if you will, on a lipid monolayer, where you see two coexisting phases, and above certain pressure, you see the two coexisting phases mix into just one. And this transition for certain compositions can be accompanied by critical behavior, which Sarah talked about, and those are the critical points. So this had already been done, and you can model these phase diagrams very easily and very accurately by considering a simple regular solution model, where you just have a simple free energy, regular solution free energy, and all you need is a repulsive interaction term. You use that, and you can get pretty semi-quantitative agreement of the data. Okay, but having the repulsive interaction term doesn't tell you anything about any possible molecular details. So luckily, we started running into more interesting phase diagrams. And they had this kind of character. That is, you had two phase regions. At low cholesterol concentrations, you had a two-phase region. Inside this two-phase region, the phases look just like the ones I showed you before. As you pass through the transition point, marked by critical behavior sometimes, those are these solid circles, then you go to one phase. And then when you go to higher cholesterol concentrations, you see something else. You again see two phases, but they look markedly different from those in the low cholesterol concentrations. And those were also marked by, and then as you increase the density, these will also disappear from two phases into one phase. These happen at much higher pressures than here. Actually, the way the probes that were used in these initial experiments underreported on these pressures. So the actual pressures are even higher. So we had, and we measured these kinds of phase diagrams for many systems. All these papers over like a 4-year period. So So what kind of model can account for this? Obviously, a simple regular solution model that I pointed out before isn't enough to do this. But you don't really need much more. And you again start with that, the same regular solution model, and all you got to do is build in a chemical reaction. That cholesterol and the phospholipid can form a complex. And the complex has an equilibrium constant, and it has stoichiometry parameters which determine the location of this cusp. So using this, you can calculate phase diagrams. So this is now like in 1999 or so, and there was this one time that McConnell was looking for me in the lab to try to tell me something about this. He didn't find me. So, so from then on, for about a year, he kept saying that I had a very high paper pressure. And I would never find me. So what he started doing was he would make copies of his lab notebooks with what he had done, and he would leave it on my desk. And I had to do the same thing and leave him stuff for him to take home. So I think this was just a subtle way of getting me to do more. But anyway, so I just have pages and pages of this writing where he's working out the theory for these, for how to calculate these phase diagrams. And he just in his papers sometimes or at least in his papers I sometimes find it hard to follow the steps as he's writing the theory, because I think he derives some pleasure out of watching people suffer through it. But in his notebooks, he's incredibly detailed, very easy to follow, and you can see he'll cross out, you can see the mistakes he makes, or very few, but you can see the assumptions he makes, what drives into those assumptions, and so I still cherish these. So anyway, so we did this, and so this was the data I showed you, and then using the simple model, we can recapitulate these phase diagrams semi-quantitatively again. So that was good. This work, these theories aren't new. Other people have thought about it for other liquid-liquid phase separation systems, particularly John Wheeler from San Diego and Caltech from Mexico. So a lot of this work was based off of that. So, okay, so now we have this framework of that cholesterol in monolayers with phospholipids can form complexes with phospholipids. McConnell introduced the term condensed complexes because we had data suggesting that the complexes have a lower average molecular area than either component alone or mixtures where they're not in a complex. So that's where the condensed complex term came. So the model makes a prediction in that depending on the parameters that you use in the model, the concentration of complex in the membrane is sharply peaked at a concentration near the stoichiometric value for a binary system. This is strictly not true for a ternary or multi-component system. More importantly, or equally importantly, is that if you look at the concentration of free phospholipid, so at low cholesterol concentrations, most of the phospholipid is free, and so you have a high concentration of that. Then it goes down as it starts getting consumed in the complex, down to a minimum value at the stoichiometric composition, and then it remains low because now the phospholipid is limiting its atom in the complex. The inverse holds for the cholesterol. So if you are to think about not the concentration of total cholesterol in the membrane, but the concentration of free cholesterol in the membrane, it shows this strong nonlinearity, which will become important as I go on. Okay, so McConnell already had this intuition, or he was already thinking about what does this mean about what does the theory of condensed complexes tell us about regions of the phase diagram where there are no phase separations? Do you need phase separations to form complexes, or do complexes always need phase separations? So this will have relevance when we get to biolayers and such. So one thing McConnell did was he took this system with this two-pump phase diagram. He prepared a monolayer mixture of the composition, which was very near the stoichiometric composition, but at a pressure which was higher than either critical point. So So you're starting off with a membrane where there's no phase separation. And then you apply an electric field to it. And the complex has a higher dipole density than either component. His prediction was that the complex would get destroyed. And then the resulting free cholesterol and free phospholipids, they happen to be in this, within a two-phase region, which wouldn't be present in the normal case because you have complex formation, then you would see phase separation. That's exactly what we saw. This is an electrode poking through a membrane, and when you turn the field on, you see these domains forming along the edge of the electrode. The electric field spread dies off pretty rapidly. That's why you only see it in a narrow region. And with no electric field, you see nothing. So this was done at a pressure much higher than the peripheral pressures. And this was consistent with complexes being present even when phase separations were not. Furthermore, it gave us some more information in the complexes. So the phase diagram only possibly tells you about the stoichiometry. In order to model this electric field effect, you needed to use you got more information about stoichiometry and about the cooperativity. So what we found is that these complexes are not just one cholesterol and two phospholipids, for instance, but rather a cooperative factor of 10 or so. So we're talking about 30 to 40, 30 to 50 molecules. And these were, a lot of this work was spurred by earlier work about the effect of electric fields on phase separations in membranes by Kai Lee, and also by Steve and Jay Brooks. Okay, another way to look at whether complexes are present at pressures where there are no phase separations is to look at the chemical activity of the cholesterol and the accessibility of the cholesterol to an extra membrane acceptor. So here's an idealized schematic of a lipid monolayer. The blue rectangles are cholesterol molecules that are free, supposedly, and the green is the cholesterol in a complex. And if the model is that the free cholesterol is more accessible to an acceptor, such as beta-cyclodextrin, which is commonly used to remove cholesterol from membranes, or other proteins or so, then maybe we can pick that up. And so that's what we noticed. This is the y-axis here is the ability of cyclodextrin to extract cholesterol from the membrane, whether it's a rate constant. And this is as we change the composition. So you see that at the low cholesterol concentrations, the extraction rate, the desorption rate is low. And then when you hit the stoichiometry, the cusp of the phase diagram, you get a 3 to 4 or 5-fold increase in this desorption rate. This again was carried out at a pressure where there is no phase separation in this membrane. So again, suggesting that these complexes are present even at pressure where there is no phase separation. This is a calculation of the chemical activity of the cholesterol, which replicates the data. So then McConnell wanted to see whether we can learn more about the nature of this reaction. And so he decided to do this desorption rate experiment at different temperatures to try to see if we can extract a heat of reaction from this. So here's again similar to what I showed before. At the lower temperature, you see these desorption rate constants are low at concentrations below the cusp composition. Then you hit the cusp composition, the stoichiometry band jumps up, in this case about 5-10-fold, and at composition exactly mimicking the stoichiometry. If you heat up the system just 10 degrees, you no longer see this breakdown, suggesting that the complexes have dissociated at this temperature compared to that. Modeling this data, we got a heat of reaction that was exothermic, and that was about 10 kilocalories per mole. So this all happened, and then we did other work on the molecular areas of these complexes, and which also agreed with and explained the classical condensing effect of cholesterol that's been known for almost 100 years. So, so the summary of the monolayer work, which took place basically over 3 to 4 years, was the experimental evidence first came from phase diagrams, and then it was verified through studies of the electric field effect, looking at the chemical activity of cholesterol, and also at measuring the average molecular areas. And what we learned is that complexes can form between cholesterol and many different phospholipids. And the complexes, one of the things they do is they strongly affect the chemical activity of cholesterol. Complexes are large, can be up to 30 molecules or so big. They have increased ordering, that's why they're condensed, and there's a sharp minimum average area. And they have large dipole moment, that's why they're susceptible to the electric field experiment. The complex formation was exothermic, and more importantly, the complexes are present at high pressures where there are no phase separations. So, yeah, you don't need one for the other now. Right? So this is summary of all the monolayer work, and then now we switch over to. Oh, sorry, one more thing. So one of the criticisms that Harden faced constantly with this work is people are always asking what are the structures of these complexes. So you can get these complexes with cholesterol. You can get it with other related sterols, like you don't need the double bonds, so that's dihydrocholesterol. You can get it with cytosterol, which has extra ethyl group on there, that's in plants. You can get it with other sterols. You can get it with many kinds of phospholipids. It wasn't particularly head group sensitive. So you can go with phosphatidylcholine, phosphatidylcholine, serine, even sphingomyelins, which has a sphingosine backbone instead of a glycerol backbone. Furthermore, you didn't even need a phospholipid. You just needed fatty acid chains, and that would enough to do. So, because of this huge diversity, it's fair to say that there may not be a single specific structure. Around that time, actually it was around 2007 or so, Mike Thayer described these extremely short-lived complexes of organic compounds, benzene and phenol, which had picosecond lifetimes. So it's possible that these complexes could be short-lived also. So a combination of these two effects could complicate efforts to try to get at the structure of this complex. However, Kai Lee has done some X-ray diffraction studies on monolayers using simple binary two-component lipid mixtures, which do suggest complexes. So maybe there is hope at getting at a more definite structure of these complexes. Okay. So then McConnell turned to the question of, do these complexes exist in lipid biophysics? So all the experiments so far in monolayers. So to do that, Sarah Keller has already talked about some work with biolayers that she has done, but Harden McConnell looked at the vast body of data that already existed in the literature. So people have been doing calorimetry studies of various lipid mixtures in biolayers for a long time. And through a series, through a lot of theoretical modeling studies, which was spearheaded by Anderson, who was in the lab at the time, they were able to show that the bilayer calorimetry data can also be accounted for by condensed complexes. And the heats of reaction that she got out of fitting the calorimetry data were on the same order as what was obtained from the monolayer data. So that was one thing in supporting complexes of biolayers. The other was Harden McConnell turned to the vast NMR data that had been generated on cholesterol phospholipid biolayers, and that had been accounted for by phase separations. This is the famous Biston-Davis study from the 1980s, where they saw broadening, cholesterol-dependent broadening of the spectra of deuterium-related phospholipids, and they interpreted the broadening to arise from diffusion between domains, various domains. In their modeling, the domains had to be small, 50 nanometers or so, and they termed the domains liquid order and liquid disorder. That's where the terminology comes from, but nobody has observed that microscopically. McConnell reanalyzed all that data using the condensed complex model, and he was able to show that the data could be equally fed by complex formation and dissociation instead of diffusion between phase separated lipids. And again, the parameters he got were consistent with parameters that we derived from the model. And then comfortably around that time, McConnell got another piece of data to chew on to see whether this model did that too. And that was these beautiful liquid-liquid phase-separated systems that Sarah Keller just described. So you don't see liquid-liquid phase separations in binary mixtures of cholesterol and phospholipids in bilayers. But in ternary mixtures, three-component mixtures, you see liquid-liquid phase separation. So this is two different systems. And this has an interesting property. So as I said again, the binary systems don't show any phase separation. So if you have three liquids, A, B, and C, A and B are miscible, each pair is miscible, but when you put all three together, you get immiscible. So these so-called closed loops or idle immiscibility curves we're seeing with lipid mixtures. So McConnell started thinking about how to model these. So he started, so he would send me emails. I don't know about most of you, but I have enough trouble keeping up with the literature from the last 2 years in the English language. McConnell would pull out these papers from 1900 in German, and from the 40s, also in German. And these are these, you can clearly see this is a three-component phase diagram. There's a closed loop phase diagram. Here's another one, and also water, phenol, and acetone. So this had been observed before. Here's three systems, probably many more, and they're seen in mixtures of common liquids or in liquid alloys. Right? The acetone phenol water system is particularly interesting. Or I found that simple. In that, so at a particular temperature, the acetone phenol, the phenol water, or the acetone water binary systems do not show phase separation. But when you put them together, what happens is the acetone and the phenol, you get a hydrogen bond here, and you get a nice stacking. You get the complex forming between these two, which has been observed spectroscopically. And that complex now has a character that's more hydrophobic than either of the components. And so that resultant compound is immiscible with water. So that's how you get immiscibility only when you have all three together. A similar argument can be made for the copper antimony bismuth or the copper gold nickel systems. So McConnell then used that line of thinking, and he applied it to this system. So he said, well, we already know from the monolayer data that the cholesterol and sphingomyelins can form a complex. And we know that the cholesterol and unsaturated phospholipids don't form complexes that are that strong. So let me take the limiting case where speaking for argument, but he took the limiting case where cholesterol and sphingomyelin form a complex, and he said that complex was immiscible with the unsaturated phospholipids. So the complex formation can be modeled by the simple reaction. He used parameters that were similar to what he got from the monolayer data, and used the same simple regular solution model that I showed you as earlier. And he was able to pretty much get semi-quantitative agreement of these bilateral phase diagrams using the simple model of complexes. So now let's move to the final part. Okay, so there's evidence that complexes are in monolayers. Strong evidence that they may also account, or it also accounts for a lot of properties of biolayers of the life itself. So he once told me as he was leaving, was Arun, black cats, black cats. All right. There's no Google or anything at that time, so I can't look up for it. So I have to actually go read a book or something. I still don't know what it means. But then he told me, he said, the hardest thing of all is to find a black cat or a dark room. There's an addendum to that especially when there's apparently Confucius who said that. So far, liquid phase separations have not been observed in live cell membranes. But until they were observed in biolayers, they hadn't been observed in biolayers either, so maybe we'll see that someday. And also, he also did a lot of work with W. Murner, and Maria was involved in these studies, single molecule studies of the IEOK proteins labeled with a fluorescent probe in plasma membranes of cells. And that also did not show strong evidence for phase separated domains. So where we are with that, we'll see where that goes. Maybe having significant amounts of protein in the membrane is important to stabilize domains in cell membranes. I mean, after all, there's hundreds of lipids that are involved. But that's kind of the state of the field now. But the idea of complexes, which I've been trying to say several times, is that it does not require phase separations. They're present whether they're phase separations or not. So it gives us a useful way to think about lipid-lipid interactions, which is not tied to phases. So the specific interactions between lipids can significantly affect their chemical activity, which is the relevant parameter for thinking about their interaction with proteins. There's a lot of interest in proteins that can measure the cholesterol levels in cells. So these are proteins involved in the cholesterol regulatory network. A lot of them discovered by Brown and Goldstein. And these proteins can detect small changes in the level of cholesterol in membranes. And so McConnell was thinking about this, and in these papers, this is a diagram that he drew in this paper, and he proposed that these studies suggest that the chemical activity of cholesterol shows a strong nonlinear dependence. And so if the cell membrane is set in such a way that it's sitting right at the edge of this precipice, then that could be a sensitive regulatory mechanism. And so what was known at that time, what is still known, this is still the high resolution structure of the cholesterol regulatory network. The machinery which controls the cholesterol levels in cells acts at the level of gene transcription. And the transcription factor that does this resides in the endoplasmic reticulum. So it has to go from the endoplasmic reticulum to the nucleus to turn on genes. And its transport from the endoplasmic reticulum to the nucleus depends on how much cholesterol there is in the endoplasmic reticulum. So if there's too much, if the cholesterol is above a certain point, this guy remains in the ER, doesn't go, and so the cholesterol synthesizing genes go down and the cholesterol levels eventually fall. When the cholesterol levels are low, it gets transported and turns on cholesterol synthesis. However, 90% of the cell's cholesterol is in the plasma membrane. So there's hardly anything in the ER. So McConnell suggested that this reaction, which forms condensed complexes of cholesterol with phospholipids, could be a regulatory sensor, which controls whether cholesterol gets to the ER to report to the transcription factor. So when the cholesterol level in the plasma membrane is low, meaning that the cholesterol level in the cell is low, most of it is tied up with the phospholipid, so you don't have much free cholesterol, so nothing goes to the ER to signal. The cholesterol level rises above a certain point, then the phospholipids that tie it up are saturated. It's a very simplistic, speculative model. And that free cholesterol gets somehow activated, and maybe transport proteins carried to the ER to do this thing. And so we proposed that in this model. And he also made a very interesting point here, in that, as I said, 90% of the cell's cholesterol is in the plasma membrane. Very little is in the endoplasmic reticulum. There are obviously many other membranous structures in the cells which also have cholesterol, but they're going to be also going to be very low. So we wondered how the cholesterol in the cell could be at an equilibrium, if you will. Like, what is stopping everything from just going into the cell, going into the other membranes. And so he also proposed that even though the concentrations are different in different membranes, the chemical activity, which after all is what is equal at equilibrium, could be the same in all membranes. That is, the chemical activity in the endoplasmic reticulum is low because the amount of cholesterol is low. In the plasma membrane it's low because most of the cholesterol is tied up in the phospholipids. So it's the amount of free cholesterol which is the same in every membrane. And another thing that simple model told us is all you have to do is set the cholesterol concentration in one membrane, and that will determine the cholesterol concentration in every membrane. So all you need to do is control it. So this has been a fascinating starting point, which is forming the basis for many experiments by cell biologists and membrane biologists. To McConnell's point that the chemical activity in each membrane could be the same, there's been some recent data to that point. So in one study, the endoplasmic reticulum membranes from hamster cells or rat liver hepatocytes were purified, and the accessibility of cholesterol, the chemical activity of cholesterol in those membranes was measured using a protein that binds cholesterol. And it shows this strong sigmoidal behavior with a break point at about 5 mole percent cholesterol. So remember that 5 mole percent is not even on the diagrams for the model membranes that I showed, but the endoplasmic reticulum is a very low amount of cholesterol. Okay? When the same experiment is done with isolated plasma membranes from these same cells, you again see a sharp threshold-like dependence, except the threshold is at about a point where 1 in 3 lipid molecules is cholesterol. So the cholesterol levels in these cases are changed by growing the cells in different kinds of media or with drugs. And what's really interesting is the resting point of the cell happens to be these green points. So even though the cholesterol concentration in the endoplasmic reticulum is 5 mole percent of the total lipids, and the plasma membrane cholesterol is about 35 mole percent, their chemical activities are identical. Something McConnell said very simply using data from models. So that's all I had to say about this last part. In his last 3 papers, McConnell also talked about how being near critical points, as Sarah said, or near threshold points like this could play roles in solvation of membrane proteins, which remains to be seen whether that will be true, but probably will. So I'll stop and I'll say lab members during this period, including some that were just before. Here's a list of them, and we were all lucky. It was an incredibly productive period, and all great ideas and concepts that McConnell was constantly cooking up.
So thank you. We have come to the end. And I just wanted again to thank all these people. It's kind of unbelievable how smart all these postdocs are. And this is a perfect example. And of course, Harden was smarter than all of us, right? Just one little story. He would often walk into my office unannounced and he says, I have a question. This was a sinking feeling of dread. No idea. And usually it would come down to something like it's either A or B. Once I figured out what the hell he was talking about. And I was sure it was A. And I would always say B. You would look at me and say, you're so smart. You always get the right answer. And he knew the right answer, and I only knew it by difference. Because he was just so much smarter than the rest of us. I think that's just fair to say. And his impact, well, you've seen it. And it's really remarkable when you listen to Arun's story. He didn't tell you some of his own work that's happened since. This exploits some of these ideas. And these ideas, I mean, this doesn't sound like malonic acid. It's gone a very, very long way from these very early ideas into something completely different. And so, you know, especially for students here or young faculty like Arun, I mean, it's just, where will Arun be in 50 years? I mean, that's the interesting question. Maybe he'll be working on a lot of acid, I don't know. So, again, let me just thank my co-conspirators, so Alvin and Hayes, who started off the day and did such a wonderful job, not only of keeping in close contact with you over the years that Harden was ill, but also in helping to organize this and bring everybody together. I don't think it would have happened without them. They just are very, very persistent. And several people have asked me, well, so how is it going with this fundraising drive for the Harden McConnell annual lecture? And I would say the answer is there will be a Harden McConnell annual lecture. It's absolutely certain, and I want to thank I'm not supposed to mention names, but some of the people are here who have made very, very nice contributions. We don't want you to stop, we want you to continue, those of you who haven't. But the fact of the matter is, I think we now have sufficient resources to have a Harden McConnell lecture in physical or biophysical chemistry in perpetuity. So that will continue. I was talking to Bien Chao about it. I don't know if she is still here. Bien Chao just got promoted to tenure. Should congratulate her about that. And she'll be one of the people who will be helping to organize this in the future. And she'll probably introduce the 2060 Harden McConnell lecture when probably most of the people who are here now won't be around anymore. So thank you very, very much for coming. There's a reception outside. Some of people coming to dinner as well. And we'll all be getting together and smiling.